Okay, good morning, Astronomy 1020. Welcome back to our second lecture. This is lecture 1, part 2, and we're going to do homework number 1 today. And with that in mind, how many people brought their Casio calculators? Let's show them up here. Ready? Come on. Who else has got them? I hope you guys brought your Casios today.
Mine is in transit. It was ordered.
Sorry, what's going on here? You're disturbing Michael Jackson. What's happening?
I said mine is in transit. It was ordered.
Oh,
Yeah, mine's doing the same thing too.
Yeah, same here. Amazon's like 9 stops away from me. They're being dickheads right now.
Yep.
Yeah, mine says 9 p.m. the latest.
Okay.
Mine's actually supposed to be right now at 11:30, and they're nowhere to be found.
Put a note in the door saying, "I'm in class, you bastards, and I need this calculator. Knock loudly." Okay, so
I got you. I'll have it before class ends.
Okay, yeah, because today we're going to really get into it, and each day I'm going to be training you on this thing, and probably one of the biggest piece of advices that I can give you is when I do these exercises in class, and I'm going to show you how to push the buttons. You really have to push the buttons yourself to learn. That's how it goes. So pay very close attention if you don't have your calculator, but the sooner you get it, the better, okay? And that goes for all you trolls out there who I can't see. You need to be punching. Sorry?
Nah. Somebody else is in class next to me.
Oh, that's okay. All right. Yeah, it be like that sometimes. Okay, so let's see here. I've hidden trolls, which is good. And I want to try to get right into it so I don't have too much dead air. I've been noticing that's something I need to work on in my lectures. In our last class, which had a lot of hiccups and things, thanks for putting up with it. I should have fixed a lot of the problems that I had with the focus, and I know how to hide trolls now. So I'm back in the saddle. I'm feeling like an experienced ranch hand. We should have ended our class last time on scientific notation. Is that correct? And then we did a lab 1, which you hopefully have turned in by now, a simple lab where we just practiced multiplying and putting some numbers into scientific notation. I also talked to you guys a little bit about rounding and the art of measurement. Those skills will come in handy as we go forward. Today, what we want to do is we want to learn a few other critical basic techniques that are going to help us going forward. And we'll also kind of get into some astronomy stuff a little bit. So why don't we go on over to our slideshow? I'm sorry. Before I do that, 1 or 2 more announcements. I realized when I was sending out the link to my classes yesterday and the day before that people are adding the course and subtracting the course, and the email list that I had is not remaining accurate. So I think what I'm going to do, one of the big pushes I'm making with this semester is I want a single schedule for all of my 1020 students for sanity. And I also want a single Blackboard page or something like that. I'm going to see if I can consolidate. It's kind of crazy, but I want to see if I can consolidate my day class, my night class, and my online class into one Blackboard page. That way I can just post one announcement and everybody gets it. Now, later on, when we all kind of go back in person, I still think we can handle that because any special announcements I make, I can post once. I'm terrified that because I have to do everything 3 times, I'm going to forget to say one thing to someone or something like that. So I hope you guys can see the logic in that. That's also why we designed a course schedule that's the same for all 3 classes. This is a new experiment with me. So, okay, so keep in mind I might do that. And if you can think of any reason why I shouldn't, please let me know. Let's get into it. I'm going to share my screen here, and we're going to go over to our PowerPoint. And this is our first, lecture show here. We're going to be learning a bit about numbers and space and some vocabulary terms so that we can sort of talk to each other about how stars move across the nighttime sky. Loosely follows chapters 1 and 2 in the Cosmic Perspective textbook, okay? So here's a picture of a beautiful constellation, Orion. You might recognize this. It's up in our nighttime sky currently in the wintertime. I noticed it last night, actually. And we want to be able to have a common vocabulary to talk about how stars move across the sky, We have to learn about angles. You can also see that even in a single photograph like this, there are thousands of stars that you can see with the naked eye or with a telescope. And so we need some more skills on dealing with large numbers of objects. I think we talked about this last time, but at this point, you guys should know the difference between a solar system and a galaxy, correct? Did we discuss that? Okay. So just remind me one more time. Solar system versus galaxy, what's the difference? I just want to make sure we know stuff, you know?
The solar system is confined in the sun's magnetic field, and the galaxy is just a combination of like everything.
Well, not everything, right? Everything means something different to me than it does to you. When I think of everything, I think of the whole freaking universe, right? All the galaxies and the quasars, but the galaxy is a collection of stars and gas, and the stars have little solar systems around them. Okay, all right. There are structures beyond the Milky Way galaxy. In other words, David, right? If you zoom out from the Milky Way galaxy, you find that there are a bunch of other galaxies. Like this is what's called the local group of galaxies. The local group of galaxies consists of the Milky Way, that's our big ass spiral galaxy, Andromeda, another big ass spiral galaxy. They're separated by a few million light years. And then they've got these little dirtbag galaxies which orbit around them and pass through them, like the Magellanic Clouds and these other small elliptical galaxies. Oh, I'm sorry, Triangulum is part of the local group too. And these three main galaxies and their little dirtbag galaxies are part of a structure called the local group. It's a large scale structure phenomenon. And there are structures beyond this. If you keep zooming out, you discover that there are clusters of galaxies. So if our little local group is a bunch of galaxies over here, each one of these dots represents a galaxy, and they're distributed on large scales in these kind of creepy filaments and voids and bubbles. Sometimes they call it pancake structure. The universe is whack, David, and it's full of a lot of strange galactic structures. If you can keep zooming out on the largest scales, all of these bubbles and voids tend to sort of smear out into a fine paste of galaxies, and they make up what we might call the observable universe. Those are all the galaxies we can observe in the time that the universe has had to send light to us. In other words, light has a finite travel time. Oh, whoa, check out that kitty, Caitlin. What's your cat's name? Let's talk kitties for a second.
That is Junior.
Where's our kitty?
He is my half Maine Coon, so he's larger than most cats, and he likes to be my desk buddy.
Oh, larger than most cats, huh? Well, I've
Yeah,
got something to share with you here. Let's see, let's go to speaker view. Oh, wait, where's me? Yeah, Jordan, give me that guy. Oh, this is a 25-pound Maine Coon. This is Phil. Hey, what's up? Say hi to Astronomy 1020. We ready to learn today? Do you have your Casio FX260 solar calculator? Oh, yeah, look at those guys, huh? Oh, shit, he almost kicked out of the computer. Here. All right, Phil, you're a good sport. All right, I love it when you guys show me your animals. That's fun. And if you live in a barn or something, we want to see chickens and lizards. We want to see all of it, okay? That's part of the fun of pandemic learning.
Yeah,
Okay,
I have two
so
more cats and a dog.
What's the Maine Coon's name, Caitlin?
His name is Junior. I call him Jun for short.
Uh-oh, Mikey's got a puppy. You know we're going to have to see that puppy, Mikey. That's important, okay? All right. Anyways, we're going to start somewhere a little more quotidian. Now that we know that there's, lots of large-scale structures, we want to start talking about how the nighttime sky works, and that's going to require us to think a little bit about the orbit of Earth. I still haven't made it over to CCRI to grab my cart of fun astronomy demos, which if you've ever seen me live in campus, you've seen me pushing around my cart full of demos. But I do have a crappy little, sorry, I'm trying not to knock over the classroom here. A crappy little Earth globe here that I can use temporarily, okay? If we look at the Earth from the orientation of space, okay? Let's say that the camera, which is you guys, let's say that's the sun. Earth has an orbit around the sun, which is quasi-circular. For now, we'll kind of pretend it's a circle, but it's not. And if you think about the Earth-Sun plane, which I'm going to define as the ecliptic in just a moment, Earth's axis is sort of tilted with respect to the ecliptic. And we can sort of define directions in space, okay? So anything in the direction of Earth's North Pole is going to be northward in space. And anything in the direction of the South Pole is going to be southward in space. And it turns out we can even do east and west, and I'll show you how we do that in a second. But let's imagine this is the spinning Earth, okay? So here's Earth spinning on its axis. Now, I'm being very particular about the way I spin this globe. You'll notice that if you guys are looking down from the North Pole, you're looking down the North Pole of Earth, so you guys are north of the Earth right now. You'll notice, and hopefully Zoom is not screwing up the left-right orientation here, but I'm spinning this globe counterclockwise. And yes, it's counterclockwise in the video too, because it's going opposite the direction of a clock. So it looks like I've flipped that switch so that you guys have the right orientation. So Earth is spinning counterclockwise in space, as seen from north or above. And it also orbits the sun counterclockwise, okay? So it's going around like so, okay? And those give rise to two different time periods that we have. The spin of Earth's axis gives us our 24-hour day, and the orbit of Earth around the sun gives us our 365-day year. And I want to start with some considerations like that. Let's take some notes on the orbit of Earth. So this section of your notes will be titled Earth's Orbit. And we're going to start with a few basic facts that you probably already knew about, all right? So we have the axis spin of Earth, and that gives rise to a day. 1 day is equal to 24 hours. Now, although most people already know that, I'm still going to go ahead and I'm going to put a box around it, because this is your first example of what is called a conversion factor, okay? Conversion factors play a big role in this class, in all physical science classes. And I'd like to start with a conversion factor that you already know so that you're not getting tripped up on the concept here. Conversion factors relate one set of units, like days, to another set of units, like hours. Anytime I write a conversion factor down, that's a big deal, and you should write it down as well. And you should try to use the same notation that I do for units. I tend to box conversion factors to remind you that these are important things that you're going to want to find later. Obviously, you don't need to memorize that, but there is going to be more coming up that you do. So we have the axis spin of Earth, okay? And then we have Earth's orbital. And for the benefit of those who'll be taking Astronomy 1010 as well, it's the orbital or sidereal period of Earth. And that means basically around the sun. When I say orbital period, I'm usually referring to Earth's rotation around the sun. And that gives rise to a year, which is 365 days. It's actually a little more than that, but we won't get into that just yet. We'll just keep it at 365 days a year for now. Notice that my abbreviation for days is a little d. I don't always stay consistent with that. Sometimes I write out day. Okay. I also mentioned, let's see here, that we have orientations in space, right? So if we have Earth's North Pole in space, that points north in space. And I won't write it down, but the South Pole obviously points south in space. It turns out that we can also define east and west in space as well. Let's take a look at the globe here. So I'll rotate so that we can see America, okay? And here you can see the west coast of the United States, and here you can see the east coast. You'll notice that on my globe, east is pointing in this direction, okay? Towards that side of the screen. However, if I spin 12 hours, half an Earth's rotation, Now, the east coast of the United States points in that direction. So it looks like east and west are all messed up in space. But there's a smarter way to do things. If I could imagine a little dude, what could I use for a little dude? Maybe this little dice or something, okay? If I put a dice where we are in Rhode Island, okay, and I imagine spinning Earth, this dice is always spinning in an eastward direction because east is in this direction at one point, then it's into the plane of the board, then it's to your left, I guess, it's my right, and then it's into the plane of the board. And it turns out that it's a really smart idea for us to define the spin counterclockwise as east. This is something that's not obvious at first, but once you think about it, it starts to make better sense. Because we define east and west in terms of a geography on a spinning globe, if we try to translate that into space, east becomes counterclockwise in space. Let's write that rule down. That's a good rule to just sort of memorize, okay? In space, counterclockwise is defined as east. You'll notice that I've used the triple equals sign. That is more powerful than the double equals. It means we define it as such, no arguing about it. Of course, that's going to presume that clockwise is west, but I'll assume that's obvious to you guys, okay? Okay, so we've got the axis spin of Earth, we've got the orbital period of Earth around the sun, and we've defined north, south, east, and west in outer space. What else do we want to do? We want to take a look at a couple of vocabulary terms here. Let's go to my slideshow. The orbit of Earth around the sun is really close to a perfect circle, but it is not a perfect circle, okay? It has a quasi-circular orbit where there is a closest approach to the sun, which we call perihelion, and a farthest distance from the sun, which we call aphelion. And I'd like to take some notes on that. And I'd also like to take some notes. Let's see here. By the way, this picture shows us the axis spin as counterclockwise or east. And notice that Earth also makes an eastward journey or a counterclockwise journey around the sun. I'd like to start off by defining a very important term in our class called the ecliptic. It's a fancy vocab term to describe the path of Earth around the sun. Here's a picture showing you the ecliptic path shown in dark blue, the quasi-circular orbit of Earth, and the ecliptic plane, which could be defined as a sort of tabletop, a two-dimensional surface connecting the ecliptic path to the sun. Let's take some quick notes on those because those are new vocab terms for most people. I'm erasing here. I usually try to ask if anyone has any objections because I know I write, people might be catching up to me here. Gonna erase. All right, let's define a few more terms. So we have something called the ecliptic path. And this is going to be the first of two definitions that we use for the ecliptic path. The ecliptic path, for starters, is basically just the almost circular path of Earth around the sun. And I can also define the ecliptic plane as a 2D surface made by the ecliptic path. Man, I don't have a hula hoop here. That would be nice if I did. But if you think about, I happen to have a ring of tape handy, right? Sorry, guys. I like to keep my phone on in case people are having trouble getting the link or need to get in touch with me, but it doesn't look like that's what this is. If you have a circle and you orient it in space, that kind of defines a plane, right? Here's a circle. If I twist it like this, that's my plane. If I twist it like this, that's my plane, right? So just a circle in its own self defines a two-dimensional surface. One of the things that's interesting about the ecliptic plane is if you look at the orbits of the other planets in our solar system, they orbit the sun also to within a small number of degrees of the ecliptic plane. And I can demonstrate that by just grabbing a picture from the internet here. Let's type in orbital inclinations of the planets, okay? And we'll grab an image because those are easier to understand. And if you look at this crappy little cartoon here, you'll see that to within a few degrees, there's a tiny bit of randomness here. The planets are also orbiting the sun on quasi-circular orbits that are really damn close to the ecliptic plane. So we define the Earth-Sun as the ecliptic plane, and relative to Earth-Sun, you know, Mars is off by about 2 degrees, Jupiter's off by about 1 degree, Uranus about 1 degree, Neptune 2 degrees. The real weirdos are like Mercury's inclined by 7 degrees, which is pretty extreme. And Pluto is probably the most extreme. It orbits up and down by about 17 degrees. But if you ignore Pluto and Mercury as weirdos, most of the other planets are kind of orbiting the sun in the same plane. And that's why when we draw the solar system, you know, in these pictures here, let's go back a spell. Oftentimes when we show the solar system like this, we're showing the planets in an alignment because they're orbiting very close to the ecliptic plane. And the point that I'm trying to make to you guys is the ecliptic plane is kind of like the disk of the solar system. Before I move off this topic, there's one other way we can look at the ecliptic plane, and this will become more important in our subsequent lectures from now. But let's just tease you with it, okay? Yes, we can see the ecliptic plane as the path of Earth around the sun. That's probably the easiest thing to do. But remember that we don't often get the outer space perspective. Normally, we're not flying in outer space in our spaceship, although we like to pretend we are. We have to observe stars from Earth, from an Earth-based frame of reference. And if you do it from the Earth frame of reference, the sky seems to rotate overhead. And the sky is rotating on something that we call the celestial sphere. You might remember that I had a little model of the celestial sphere that I like to use for my lectures. Maybe we'll define this in our next class with a north celestial pole and a south celestial pole and a celestial equator here. If you're in an Earth-based perspective and you're watching the sky rotate overhead, the ecliptic plane or the ecliptic path can have a secondary meaning. And the secondary meaning is this green line here. It's the path that the sun makes as it travels against the background stars, not during the course of one day. I'm not talking about the east to west motion because that's a rotation of Earth thing. I'm talking about the yearly motion of the sun against the background stars. That's also the definition of the ecliptic. So the ecliptic means two things at once, and that can be confusing. Let's write it down. The ecliptic, definition number 2, is the path of the sun against the background stars. And by the way, so that we don't confuse it with the east to west motion of the day, maybe we should put in parentheses, it's the yearly path of the sun against the background stars. Hey, doesn't that remind you of something that we talked about in our lecture last time? Hey, Amanda French in the background with the badass vocab terms. That's right. The ecliptic is the zodiac, and the zodiac is the ecliptic. Let's write that down. The ecliptic is the zodiac. And Amanda, that's very important to astronomers, right? Because, you know, Vishnu wasn't kind enough to paint the ecliptic onto the sky for me. As an astronomer, if I want to find the ecliptic on my sky, I look for those well-known zodiacal constellations. I think I even have a slide to that effect. Hold on. I think I have a slide showing the path of the sun. Yeah, 62. Don't often use this one. Throughout the year, the sun is traveling through the constellations of the ecliptic. And not only that, but at nighttime, let's say I look up and I see Mars in the sky. I know Mars is going to be in one of these zodiac constellations. So I usually try to say, oh, is it in Libra? Is it in Sagittarius? Honestly, it makes me sound like one of those astrology smokers, but it's really just me keeping an eye on the nighttime sky, right? It's just the sun traveling through those constellations. So you can use the, that's okay, Amanda, we're cool. I don't mind if there's some trolls, as long as, you know, luckily we've got a few people hanging out with me here. So nice to see all you guys. And if you're a troll, chime in just like Amanda did. I love it, okay? Okay, so now that we've defined the ecliptic path, let's talk about 2 points on the ecliptic. They're the points where we are closest to the sun during the year and farthest from the sun during the year. And those terms are called perihelion and aphelion. There's only a slight difference between perihelion and aphelion, but things happen because of it. So let's talk about it. Note time. I'm going to erase this, students.
Wait, hold up real quick.
Yeah, sure. One of the nice things about watching the videos is you can probably pause it to take your notes. Whoever asked, just let me know when you're done.
I'm done.
Okay. Okay, so key points. In Earth's orbit. First of all, we have perihelion. That's the point in orbit closest to the sun, okay? Mikey, it's posted online right when it uploads to YouTube. It usually takes me 2 hours to render the video, so I tend to post it around 5 o'clock or so. And I start processing the moment lecture ends. So I'm doing it as quick as I can. Point in orbit closest to the sun. Then we have aphelion. That's the point in orbit farthest from the sun. Perihelion and aphelion are key vocab terms that I'm going to want to use with you. There's a couple of other vocabulary terms, sorry, I'm trying to keep my head out of the way, that we're going to want to use as well. Let's take a quick peeksy-weeksy on our slideshow. Okay, so first of all, function F523. Earth's axis, north-south axis, is not perpendicular to the ecliptic. It's tilted by the infamous 23.5 degree axis tilt. And there's a whole lot of stuff that is dependent upon this 23.5 degree axis tilt. One of them, for instance, is the change in seasons. One might naively think that the changing distance between the sun, perihelion versus aphelion, is the cause of the change in seasons. But actually, perihelion, that occurs in January. So we're actually close to perihelion right now. and aphelion occurs in July. So the changing distance has nothing to do with the seasonal changes. The seasonal changes are all caused by the axis tilt. And in fact, globes often reproduce this 23.5-degree axis tilt. That's not to give you a better look at Madagascar, okay? They're trying to show you the orientation of Earth with respect to the ecliptic plane, because stuff depends upon that, okay? For instance, there is one key day in the year, and let's call this the summer solstice. That's the day when, if you are the sun, so here's you, you're the projector, you're the sun, and you're looking from the eye of Ra out into the solar system. There is one key day where Earth's North Pole is tilted most directly towards the sun. And that day is called the summer solstice. A day before, a day after, the alignment is not perfect. But on the day of the summer solstice, that's when the northern hemisphere points most directly towards the sun, and sunlight beats down most directly on the northern hemisphere. And there's also a day called like the spring equinox. That's the day when the North Pole is perpendicular to the sun, which is you. And that's the day when Earth's equator is pointed towards the sun, okay? If my camera illustrations are failing you here, why don't we look at a cuter diagram of this here. So this defines 4 key points in Earth's orbit, and there are certain days of the year they correspond to. The spring equinox is where, let's see if I can get some drawing tools here. On the spring equinox, the axis tilt is like this, but if you think about this in 3D, it makes a 90-degree angle with respect to the sun. The equator points towards the sun. Here on this day, the North Pole is tilted towards the sun. That's the summer solstice. Now we have the fall equinox, and then we have the summer solstice, the winter solstice, where the axis tilt of the North Pole is tilted away from the sun. Geez, it's kind of hard to talk about this stuff. It's like a 3D diagram-y thing. Let's take some notes on it, okay? So there are 4 key points in orbit. We have the spring equinox, and that occurs close to, but not always, around March 21st. We have the summer solstice around June 21st. We have the fall or autumnal equinox. That's around, September 21st. And then we have the winter solstice. That's December 21st, okay? And these are 4 key points that make different alignments with the sun throughout the year. They're also responsible for changing seasons.
Is that where we get like on our calendars? Is that where that comes from for like on our calendars, like the first day of spring, the first day of summer?
Okay, well, there's a sort of funny sleight of hand going on there that most people are not thinking about. Let me just stand aside because I can see people are still writing there. Caitlin, I was tempted to go there, and now you've broken the seal. You've made me discuss these secret machinations, because I think it's something that people are interested in.
Before you move on to that, can you tell us as far as the summer solstice, winter solstice, and the equinoxes, which season is correlates to whether it's the north or the equator or the south is pointing towards the sun?
Yeah, so this is a northern hemisphere bias, which is in a way okay because most of the continental landmass that humans live on is concentrated in the northern hemisphere. So, okay, I guess we're being terrestrial chauvinists and we're prejudiced against our Australian friends and our Kiwis and our South American friends, but those people are just kind of used to it. They know that they call like their Christmas time is summer. And that's when, if you're in Australia, you put shrimp on the barbie and you go swimming in the beach in Christmas time. It's still Christmas, but they call it summer. But they know that everyone else in the Northern Hemisphere is calling it winter. So I figured I wouldn't go there, but I do have a student in my other class who's from New Zealand. So I should be conscious that there might be others out there with similar backgrounds. Yeah, but this is all from a Northern Hemisphere perspective. But I think if you're going to talk to astronomers around the globe, everyone's still, okay, so let me say this. They still, if you're in Australia, you might call it summertime in December, but it's still referred to as the winter solstice. Does that make sense? A little confusing, but everybody calls December 21st the winter solstice. They all agree to have a Northern Hemisphere bias for the sake of discussions. Okay, hopefully that answered the question. As to the first day of spring bullshit, like, let's think about what's going on here. Actually, the day that should be the warmest day of the year, or the warmest month of the year, should actually be the summer solstice, right? The day when the sunlight beats most directly down on the Northern Hemisphere is June 21st or 22nd. The dates shift around a bit because there's not exactly 365 days per year. Because we have leap years, the day of the solstices is constantly changing, right? So let's see, we're in January now. We're headed towards the spring equinox. Oh shoot, I gotta get rid of that. Come on, that's not what I want. I don't know how that came up. What was I trying to get here? Gosh, I'm blank, guys.
Spring equinox.
No, I want to look up spring. I keep hitting funky buttons. Spring equinox 2022. That's what I want to do. You'll actually notice that this year, the spring equinox, okay, there's my annotate. Let me clear the drawings. This year, the spring equinox occurs on March 20th, on Sunday. And if we do 2023, oh, it's also on the 20th, 2024. Whoa, actually, sometimes it's on the 19th. That's crazy. Almost never on the 19th. 2025.
I actually got a question about that.
Yep.
You know how usually certain days change throughout the year? For example, like Halloween will fall on a Saturday, then it will fall on a Friday. Why does that happen? It always confuses.
That's got more to do with the orbital period of the moon. Wow. I was thinking it was going to be a little more straightforward, where it was going to iterate between the, usually it will be the 20th, the 21st, the 22nd, or the 23rd, and then it resets or something. But that has more to do with the phases of the moon than it does in the way we define a month, because a month is loosely based on phases of the moon, but the moon's period does not line up with a calendar month, right? Not perfectly. So moon phases 2022. Let's see if we can get a nice calendar here. Well, okay, every aspect of timekeeping is related to astronomy, right? The year is based off the orbit around the sun. Months are based off the moon, and we have 7 days of the week based on the different planets. So it's just about the fact that there's not an even 30 days in every month. Seven doesn't divide into 30 perfectly evenly. There's all kinds of reasons for it. To be honest, some of the nitty gritty of timekeeping like that, I do get into in my astronomy 1010 class. But because
I got you.
Oh wait, Lionel, was that Lionel asking that question?
Yeah, that was me.
Lionel,
Yeah, I have your class.
Lionel, you're also taking 1010 this semester.
Yes,
Let's
sir.
save that discussion for 1010 because it's going to be way more relevant there. And so probably by next week, you're already going to understand the answer to that question. So stay tuned.
It sounds great.
One thing at a time. Okay, so I got this stuff. Okay, let's just leave all this here for now because you guys are asking interesting questions, but it's tempting me to go off on a flight of fancy here. I can do that sometimes. Okay, what we want to do next is we want to define some astronomical distances, because as interesting as timekeeping and the solar system is, we're here to discuss stars and galaxies. We kind of want to get the hell out of our solar system. And that means we have to think about giant distances and how we travel between them, okay? So let's go ahead and let's define a very important vocabulary term. It's called the astronomical unit. because there's a changing distance between Earth and the sun, it's very helpful to define something called the astronomical unit. It's the distance between Earth and the sun. Oh, I guess I'm going to define it in terms of kilometers. So maybe we should just have a quick chat about the metric system too. Can I erase this, everyone? All right. So let's do a thing on astronomical distances. Let's start with a small distance. The meter is our gold standard for measuring distances in the metric system. I showed you a meter stick in our lecture last time. It's close to the size of this board, and you'll remember it's also about the height from my foot to my leg. This is also proof that I'm not one of those professors who teaches class without pants on. Okay, so meter stick, the distance from foot to belt. Okay, everyone always asks me that. They're like, "Oh, so you teach your class without your pants on, right?" The meter is our gold metric unit of distance, but meters are good for measuring the heights of a person, right? The average height of a person, a human, is approximately 2 meters tall. Okay, that's a way to think about it. All right. To measure distances like around the planet, say from Rhode Island to California, it makes more sense to make use of the kilometer, right? And you guys remember we defined kilo as 10 to the power of 3. So 1 meter, sorry, whoa, 1 kilometer is 1,000 meters. Let me try that again. Is 10 to the 3 meters, which is another way of saying 1,000 meters, okay? For distances between the planets, the kilometer is not sufficient because you suddenly need sometimes millions and even billions of kilometers to measure the distance from somewhere like Earth to the distance of Neptune. And that's where we want to come up with a larger unit of distance called the astronomical unit, which could be defined as the average distance between Earth and the sun. 1 AU is about equal to 150 million kilometers. Now, we have a rule in this class that I should have mentioned during our first lab. The rule goes like this. Any number which is greater than 1 million must be in scientific notation. Okay? I've used some abbreviations there.
I think you did mention that.
Excellent. Okay, I was starting to question myself here. That's a great opportunity for us to practice our scientific notation skills. Does anyone want to try to put that into scientific notation for me?
Would it be 15 to the power of 6?
That doesn't make sense because if my decimal point is here, if you want to move, first of all, okay, Amanda suggests 1.5 times 10 to the 8. That's more proper. So I just want to show you how she did that. The decimal point's there. She wants to move it between 1 and 5, so she has a single lead digit. And that means you'd hop 1, 2, 3, 4, 5, 6, 7, 8 places. So if you're using proper form like Amanda does, 1 AU would be 1.5 times 10 to the 8 kilometers. Now this is okay. This is good. This is proper form. Now, if you look up the definition of an AU in the book, they're going to put it in proper form, right? So in your textbook, there's always a spot in every astro or physics textbook at the end where I can hear, hey, let's find out who's got the paper cracklins. I love it when you guys contribute and you don't have to raise your hand or anything. Just try to mute so background TVs and stuff don't get, oh yeah. Hold on. In the back of every textbook, they usually have like important conversion factors and numbers that you might need. So if you look up astronomical distances, I fixed my focus so it's hard to focus. They'll put 1 AU as 1.5 times 10 to the 8 kilometers. They kind of do, they do the same thing. But to the person who said 15, let's say you wanted for some reason to only move the decimal point there. That would be okay, but your power would not be 8 anymore. You'd only have moved it 7 places. So if you wanted to do what you were trying to say, you'd do 15 times 10 to the 7 kilometers. And that's weird, but okay. Is that how you spell weird? I have troubles with I's and E's. What's wrong with me? I guess I'm weird. Okay, yeah, that is how you spell weird. All right. In fact, I'm so weird that I don't even like to move my decimal points to the 15. I actually prefer to move it 1 stop earlier than that. Watch this craziness. Okay. 1 AU could also be written as 150 million kilometers. And this, my friends, this is good math style, okay? And that's how you're often going to see me writing 1 astronomical unit. That's my favorite definition of the astronomical unit. And the reason why I tend to jiggle the decimal point around is I like to get to the point where my power of 10 is either like a 10 to the 6 or a 10 to the 9 or a 10 to the 12, because then I can read it in my mind as 150 million kilometers. Remember that chart we made at the end of last class? For me, 10 to the 6 means a million. They're the same thing. So I can read this in my mind as 150 million kilometers. That's more elegant than 1,500,000 kilometers. You see what I'm saying? Okay. That's, by the way, you can also put this into your Calci and try it out if you've got a Casio. If you type in, watch my moves here. If you do 150, and remember, we just use EXP for times 10, EXP 6. Now you don't have to hit equals, but if you did, boop, that's 150 million, okay? The astronomical unit is really good for measuring distances between the sun and planets in our solar system. Let's take a peek. So what you see happening here is if you measure the distance to planets from the sun, Mercury's at like 40% of an astronomical unit. Venus is at 70% of an astronomical unit. I realize, guys, that hold on a second. I'm just sorry, guys. I'm just checking to make sure that everyone's got the link here. Anyways, notice that Mercury is about 40% of an astronomical unit. Venus is 70% of an astronomical unit. To go from the sun to Mars, 1.5 AU. And if we get into the outer solar system, the distances get even more extraordinary. The distance, say, from the sun to Jupiter is 5 AU. To Saturn is 10 astronomical units. Saturn is twice as far from the sun. Uranus is 20 AU. Neptune is 30 AU. Pluto's got a squishy orbit, but the average distance between Pluto and the sun is about 40 AU, okay? So the entire solar system, if you think about it, edge to edge, the disk of the solar system is about 100 AU across. And that's great because that means any distance that you would like to measure between one point and another in the solar system, is usually going to be a number between 1 and 100, and therefore easier to memorize and remember. So astronomical units are just a tasteful unit to use when you're measuring distances within our solar system. If you want to go to the next star, astronomical units start to get a little clunky. Let's tiptoe back to one of my earlier slides. Oops. So this is a logarithmic scale, meaning instead of plotting 1, 2, 3, 4, 5, we're plotting 10 to the 1, 10 to the 2, 10 to the 3. So here's 1 AU, but the next space is 10 AU, and the space after that is 100 AU. 100 AU gets to the edge of our solar system, which is sometimes called the heliopause or the bow shock. That's where Voyager, the 2 Voyager spacecrafts are. They're kind of at the edge of our solar system, leaving into interstellar space. If you want to get to the nearest star, Alpha Centauri, you have to travel more than 100,000 astronomical units away. And that means for distances between stars, AUs start to get a little clunky. That's when it's time for us to define yet another unit of distance, a distance for the distances between stars. And that's going to be the light year. Let's see if I can find that here somewhere. Here we go. Okay. So the speed of light is the fastest speed known to nature. And what astronomers do is they say, okay, if light's the fastest thing, what we're going to do is we're going to turn on our flashlight and we're going to let those photons race out into space. And at the end of 1 year, we'll say, how far did you get? And that distance, we will call that a light year. You want to be careful because even though it has the term year in it, it's a distance. It's the distance light travels in 1 year. Let's take notes on that. A light year is defined as the distance light travels in 1 year, okay? Now, 1 light year, 1 LY, is approximately 9.5 trillion kilometers. To get this distance, I'd like to show you how it comes about. The speed of light, which gets its own letter in physics, c, has a value of about 300,000 kilometers per second. That's extremely fast. That's the fastest speed allowable in nature. You can think of it as nature's, the universe's speed limit, okay? And if we want to get the distance light travels in 1 year, we can use distance equals velocity times time. That's kind of a classic formula from baby science, right? Distance equals rate times time. And we can plug in the values of the speed of light for the velocity. And actually, guys, we'd have to take 1 year here, but we'd have to convert to seconds. Okay. Actually, guys, I'm feeling a little bit schizophrenic. Before I can talk to you guys about converting 1 year to seconds, I think I'm going to have a pause, and I think we're going to actually have to try a simpler problem because I want to teach you guys a new lesson or a new skill now. Let me just check the clock and see how I'm doing time-wise. Okay, we got about a half an hour. I think I can do the things that I want to do. I have one really big lesson to teach you today, like the most important thing. It's a new skill that's equally as important as scientific notation. But I don't think I want to start doing it here. I'm sorry, I'm just going to leave this alone for a second. Basically, how many, oh, great question, Fred. The number of AU in a light year, I believe, is, oh my gosh, I should know this right off the top of my head. It's, let's see, 206, 26, it's, how can I forget this? Here, well, I would actually have us solve that problem with dimensional analysis, but I'll do it this way. It's 63,000. Let's write that down, okay? Light year is about 63,000 AU. Great question. I should have known that off the top of my head. It just took me a second to figure it out. So the distance, for instance, here's another one. The distance from the sun to the nearby star system of Alpha Centauri, that's about 4.4 light years. We're going to need that in our homeworks today, so I'm having you put that down right now. We can think of 4 light years as a typical distance between stars, okay? So let's actually write that down. 4 light years is a typical distance between stars. Fred, great question. Great thing to ask. Before I get into conversions, the way that we should have answered Fred's question is with the skill that I'm about to teach you. So I didn't want to forget to answer this, so I did it quickly. But let's talk about how we do conversions, because they're already coming up without even thinking about it. When you guys are done taking notes, I want to erase and start a new set of notes. Here I go. The right way to introduce this is with a sample problem, okay? Let's talk about the kind of problems that we're going to be solving in just a few moments when I do our homeworks. Let's start off easy. Here's a sample problem. If Pluto is 40 AU from the sun, let's ask a question similar to Fred's. If Pluto is 40 AU from the sun, how many kilometers is that? Okay, so the first thing to recognize is this is what's called a unit conversion problem. And a unit conversion problem relates one set of units, like say some number of AUs, and it asks us to convert them to say some number of kilometers. Unit conversion problems are at the heart of science classes. You constantly have to change your scale by doing this. Now, we could probably try to muscle our way through this using thoughts and common sense, but that's quickly going to deteriorate and become more difficult as the types of units that we convert become more abstract. For this reason, I have a set of skills that I want everyone to use, and I'm going to show you now how we solve these problems in our homework. For the duration of this course, you are going to do things my way. If you've got your own way, well, then that's great. Power to you. But today or this year, the semester, I want you doing things with my methods so that I know you have learned them. You are free to discard them later on if you don't think they're useful. I'm now going to teach you the 4 steps of what's called dimensional analysis. Now, this is a really important thing in this class. I want you to put a box around it. I want you to put stars next to it. And then I want you to put beams of fire and light coming off the side. Because later on, when you tell me I can't do that, we're going to have to go and hunt in your notebooks together to find this 4 steps of dimensional analysis, okay? Okay, The first step is very simple. You simply write down the number to convert with its units. The second step is we multiply by a division bar, and we usually do it like this, okay? We multiply by a division bar. The third step is we put the units in first. To cancel. So we cancel our units first. And then the fourth step is we put numbers in second using conversion factors. I wanted to get these down in your notebooks for starters, and now we'll give it a shot, okay? Please write these down, very important. In fact, put a box around the whole damn thing. You are going to want this later, just like that, okay? I want that appearing in your notes, just like so. Most important set of notes you'll take from me all semester. Fred, let me know when you're done. You're just a random person I can see writing. You're good? Does anyone object to me erasing right now? Okay. Lionel, Caitlin, let me know when you're good. It's an opportunity for me to use some coffee.
Professor,
Yeah.
I wanted to let you know I have a class at 1, so I'm gonna have to get off at like 12:55-ish.
Okay, is that Caleb? It sounds like Caleb.
Yeah, it's Caleb.
Hey, Caleb. That's fine, buddy. The first homework that we do in 1020 is a wee bit different than 1010. So could you do me a favor and just come back and make sure you watch the video so you don't miss any little tidbits later?
Yeah, no problem.
So for Caleb, and I don't know if that was Maya or whoever, I understand some of you have to go at 1.
Yeah, me too.
I get it, and that's fine, but that's why we record these, right? So I'll have it posted by 5. I always start the homework an hour and a half in, scrub to an hour and a half, and you should see me starting the homework. Follow along, copy everything I do, and then turn it in. Can you handle that?
Yep.
I think I got it.
Cool. Okay, can I erase? Any objections? All right, guys, what we want to do is we want to try these out by doing the problem that I suggested, okay? So if Pluto is 40 AU from the sun, how many kilometers is that? I want to do a couple of things here, so let me go kind of quick if you can handle it, okay? So let's start by writing the number down to convert with its units. I'm going to write down 40 astronomical units, okay? Step 2 is I multiply by a division bar. And that means I do times division bar. All unit conversions either involve multiplication or division. We're trying to keep our options open. The real secret of dimensional analysis is to put units in first to cancel. Now, if you remember from your algebra class, if you have a number like 40 AU, it might look like it's in the middle of the division bar because of the sloppy way in which I wrote it. But every number is part of a secret fraction, because I can always divide something by 1 in the dark secretly. So even though 40 AU looks like it's in the middle, technically speaking, 40 AU is on the top of my secret fraction. And that means I can get rid of the astronomical units by putting in units first and putting astronomical units on the bottom. And since I want to convert to kilometers, I'm going to put kilometers on top. This is allowable as long as I have a conversion factor between kilometers and AU, which I do because I taught it to you about 10 minutes ago, right? Now watch what happens. Just like in algebra, when you can cancel out variables, top and bottom of a fraction, AU's on top and AU's on bottom cancel out. You might not have understood what just happened here, but by letting the units guide you, you make sure that you never screw this up. So I don't ever want to see people putting numbers in before their units are in place. Okay. The fourth step of dimensional analysis is to put the numbers in last using conversion factors. This requires you to have a conversion factor in your back pocket. Does anyone have a conversion factor between kilometers and AU? And can you tell me what it is?
150 times 10 to the 6th.
Fine, but from now on, when you talk to me about conversion factors, I don't want one side of it. I want you to say it this way, my friend. Say 1 AU is equal to 150 times 10 to the 6 kilometers. Can I ask that of you?
Sounds good.
Always give me both sides of the equal sign. I've learned this the hard way. Okay, now who was just talking to me there?
Amanda.
Amanda, your job is to try to put these numbers in the right place. So this is where your conversion factor goes, right here, okay? The fraction bar is where we're going to put in the conversion factor. What number should we put on top and what number should we put on the bottom?
So 1 should go on the bottom, and
Yep.
then 150 times 10 to the 6 kilometers is top.
That's right. And it's not always going to be that 1 is on the bottom. 1 can go anywhere. Sometimes there isn't even a 1. What's important is that you keep the number next to its units, just like you see in the conversion factor there, okay? If 1 goes with AU, then 150 million goes with kilometers. Okay, now let's take out our Casio calculators and let's punch them up. Now, for those of you who don't have a Casio, I'll do this up here in front of you. We don't need to worry about dividing by 1, but everything that's on the top, we multiply. Anytime something is on the bottom, we divide, and I ignore ones. So basically what I'm going to do is I'm going to multiply 40 times 150 million, right? So I'm going to do 40 times, punch with me if you're at home, 150. I use EXP for times 10, 6 equals. And there's my answer. Hopefully you'll see this on your calculator at home when you do it. How should I write my final? You got it, Mikey? Cool. Mikey, how should I write this final answer? Mikey, you're going to regret participating here. In other words, is my answer greater than 1 million or less than 1 million?
Greater.
Then you got to put your answer in scientific notation. So someone do that for me.
It's 6 times 10 to the 9th kilometers.
Good. And how do we say that in plain English?
Is it 6 billion?
That's right. Using the chart that I taught you last time, it's 6 billion kilometers from the sun to Pluto.
Yes, sir.
All right. This seems like a simple thing, but you've just taken your first step into a much larger world. The skills of dimensional analysis will help you, not only in astronomy class, but in so many other classes and even in life. You'll see. Let's try another sample problem related to our homeworks today, and that's about building a scale model. Do I have time for this shit? I don't know. Okay. I'm going to save the building of a scale model for next time, because that'll be a fun little time suck. Instead, I'm going to teach you two more things related to our homeworks today, okay? I have to make a command decision. I've got two more little modules to do with you guys. Let's learn about a formula that we're going to want for our homework today called the small angle formula. And as a meditation point, I want you guys to think about this experience that you've probably had before. Sometimes you go out at night, maybe around Halloween, and you see a big old creepy moon, a big orange moon rising above your horizon, right? And you look up at the sky and you say to your friend, whoa, dude, the moon is huge. Look at the moon. Well, you've been the victim of something called the moon illusion, okay? Next time you see one of those big old creepy moons, one of the big orange moons on your horizon, I want you to take your finger at arm's length, okay? And I want you to hold it out and project it up against the moon. And what you're going to discover, to your surprise, is that the moon is like half the width of your index finger, okay? So your index finger at arm's length will actually appear bigger than the moon. And what I want you to do is I want you to wait until later on at night when the moon gets higher up in your sky. It won't look orange anymore, and that's sort of a optical effect due to our atmosphere. It'll kind of look white. But not only will it look, oh, of course, I get all these cheeseball pictures here. Not only will it look white, but if you take your finger out and you hold your finger up against the moon, you will see that the moon is still roughly half the width of your fingernail. No kidding, okay? And what that means is the moon's apparent size hasn't changed, but your perception of it has, because when you see the moon on the horizon, you have a foreground of things to compare it to. What I'm trying to tell you is that you do not see the size of a thing. You see things in your field of view as angles. This is not only true for astronomical objects, it's also true for just stuff in your everyday life, okay? So let's take some notes on angles and angular size. We're going to make a little drawing that looks, maybe, hold on a second here. Whoops, I don't know how that happened. We're going to make a little drawing that looks something like this, okay? This is the drawing that I want to make. So the last little module for the day, the last thing before we do our homeworks, is a module on angles and something called angular size. Let's try to imagine that we were looking at the moon from some distance away. So here's the moon. And the moon has some actual real diameter. And you're observing it from Earth. Okay, so here you are on Earth, and you're the observer. That's what we call the person looking at the astronomical object, or the observer. Okay, and the moon is going to subtend some angle on your sky. The symbol that we are going to use for angular size is the Greek letter theta. You don't have to know Greek. You don't even have to know that it's called theta. Our symbol for an angle is going to be a circle with a line through it. The Greeks loved geometry, so in honor of the Greeks, we make angles Greek letters in astronomy. So this is your angular size here. And for now, the unit that we're going to use for angular size is we're going to measure angles in degrees, although that's quickly going to change. So put in parentheses degrees. The angular size of an object is related to two quantities. One is its distance between you and the object. That will be represented by little d for distance. And for now, let's say it's distance in kilometers, all right? And that's going to be related to the size or the diameter of the object. So you can think of S as the size or the diameter of the moon. And for now, we're also going to measure that in kilometers. And what I'm going to tell you guys is everything in your field of view subtends some angular size. The camera sees angles. Look at little ping pong ball here, right? Little Mr. Ping Pong Ball is maybe about 3 centimeters in diameter, right? If I press it up in front of the camera, it covers your entire field of view, right? As the distance between you and the ping pong ball increases, the angular size of your ping pong ball gets smaller and smaller and smaller. In fact, you can often use your hand as a rough and ready angular measurement tool. And astronomers do this all the time. So if we're going to measure in degrees, F537, oh shit, sorry. Try that again. Function F, nope, that's not working. All right, click. Now function F537. Okay. Degrees are angles that represent 1/360th of a circle. If you hold your finger, here they show the pinky, but you can use your index finger. Your index finger at arm's length subtends about 1 degree. Your fist at arm's length is about 10 degrees. And if you do the Hawaii hang 10 thing, that's like 25 degrees. Here, the crappy weed smoking illustrator artists that they hired clearly does not fucking understand angular size because they have their elbow bent. Wrong. You should hold your arm outstretched for a standard length, okay? And you should outstretch your arm. They're measuring the 2 stars, the pointer stars of the Big Dipper. They have an angular separation of 5 degrees. So we can talk about the angular size of an object. The angular size of the moon is about 1/2 degree. And the angular separation of objects like the 2 stars and the Big Dipper are about 5 degrees. The angular size of an object is related to its distance and its size by a very important formula in astronomy. And I'm going to be teaching you 1 or 2 key formulas per week. And this is the big one for this week. It's called the small angle formula. You need to know this formula so that you can even understand how astronomers think and why they do the things they do. Introducing the small angle formula. There are going to be many versions of this in this class. This is the chapter 2 version, okay? And it goes that the size of an object is its angular size times its distance times 2 times pi over 360 degrees. And when I introduce a formula, I tend to do a little sample problem so that you can kind of understand what's going on here. So for example, the moon has an angular size of 1/2 degree. And the distance to the moon is about 384,000 kilometers from Earth. Those are what are called the givens. Those are the quantities that you can work with when you solve a problem. This is what we call the givens. That's just a sort of physics and astronomy term for solving problems. So given that the angular size of the moon is 1/2 degree, the distance is 384,000 kilometers, find the diameter S of the moon. In this case, our units are all sort of set up. Our distance wanted to be in kilometers, and we've got the distance in kilometers. The angle needs to be in degrees, and we've got the angle in degrees. So we can just sort of set the equation up. We always write it down first, and then we punch it up in one shot. So what I'm about to show you is how we're going to solve problems today in our homework, okay? One of the reasons we're going to be doing it together is so that you give me it in the form that I like. Okay, so S is equal to 0.5 degrees times 384,000 kilometers times 2 times pi over 360 degrees. Now, the way we're going to punch this into our calculator is in one clean shot where we punch it all in elegantly, okay? Just trying to avoid glare from the window here. Okay, that's
Excuse me, Professor. What does theta mean again?
per our diagram, and this is why we do this, theta equals the angular size in degrees. So make sure you have that in your diagram, okay? One of the reasons we always draw the diagram is so that you know what all of the letters stand for. Does that help? Sorry, my handwriting was a wee bit crappy there. That's my bad. Okay, let's just punch. Now listen, watch me punch, but if you're at home and you have a calculator, you should punch too, okay? So let's do this. So we're gonna do, this seems to be the best optimal distance. So we're gonna do 0.5 degrees times 384,000 times 2. Now for pi, there's actually a pi key in gray above EXP. Normally you have to hit your shift key before you hit the orange keys, but the gray one, the gray pi means you actually don't have to hit shift. So if you just hit times EXP, oops, sorry. Okay, let me try this again. If I hit 2 EXP, that means 2 times 10 to the 3 or something like that. But if you just hit EXP by itself, boop, you get pi, 3.14159265354, . Okay, so if I do 2 times pi, then that uses EXP as pi. So watch out for your EXP key. It's dangerous, okay? Let me try that again. So it's 0.5 times 384,000 times 2 times pi divide by 360. And boom, there's our answer. I don't know if you guys can see, but there's a decimal point between the 1 and the 0. This is what our calculator tells us. Do you guys remember how we had some common sense rules about rounding from our lecture last time? We're going to build on the stuff we've learned. What should I round my answer to? Did anyone punch this into their calculator? Did anyone get what I got?
My calculator is actually on its.
It's on its way, Destiny. Well, I'm looking forward to you using that.
Is it 3.4 times 10 to the third power?
Well, remember, our rule, Fred, is we use scientific notation when the number is greater than 1 million. Is our answer greater than 1 million?
No.
I still think we want to round, Fred. I like your rounding. I just don't think scientific notation was like necessary. So can you give me the answer again, just rounding it without scientific notation?
3.4.
Wait, Fred, I did not give you permission to molest the number. This number is not of order 1, okay? This number is of order 1,000.
Gotcha.
Fred,
So it's 3351.
That's 4 sig figs. That's too many sig figs for me. And
I'm-
also, it's not consistent with how you rounded earlier. Earlier, you rounded to 2 sig figs. Now you're giving me 4. You're confusing rounding in order of magnitude, and this is something that we need to figure out, okay? In fact, Fred, you're helping me by being weird, okay? Does anyone see the problem? Does anyone know what I want?
Would it be
You want to round it to the nearest 10th place.
No, not to the nearest 10th. I want to round it to two significant figures. That's not the same thing. I want two sig figs.
it would be 3,200 or sorry 3,400?
Yes. Who said that?
Emma?
Oh, sorry, Emma, you're so close. Hey, that cute little pink mic that you got with the kitty ears, turn that thing up, okay? You're quiet. Okay. But yes, Emma's correct. I want to round it, Fred, to 3,400, which by the way is 3.4 times 10 to the 3, okay? But 3,400 kilometers. Oh, by the way, I meant to ask you guys the units. Notice that degrees up top, dimensional analysis style, cancel with degrees on bottom. Only kilometers are left behind. Box your answer. It's 3,400 kilometers. This is how our answers are going to look in our homeworks, okay? Let's take a look at what we've done. Where's my cat laser pointer here? I got this for playing with Phil, but it could also be useful here, okay? Now look, the way we do problems is we take the formula and we set it up, plugging in the numbers with their units. I don't want to see any intermediary steps besides that. I want you to punch it into your calc in one clean shot. I want an answer with its fucking units. I want scientific notation when appropriate, Fred, and I want you to round to two sig figs. That's how we do business in this class, okay? Now, we're just about to start our homework, so I'll give you a pause before there, but there's one last thing I got to do with you, and I'm probably over budget here because I'm always over budget. Fuck, it's 103. Okay, last little bit, because this is part of our homework today, okay? I need to erase this, and I kind of need to erase it now. Can I please do that? All right. It turns out, my friends, that degrees are kind of clunky units to use in astronomy. And that's because the angular size of the moon, as you just learned, is, let me write this better here. The angular size of the moon is about ½ a degree. By a curious coincidence, the angular size of the sun is also about ½ a degree. And that's pretty cool in a way, because what it means is the angular size of the sun and the angular size of the moon, the sun and the moon are not the same size, right? The sun's way bigger, but it's also farther away. But the two of those things perfectly cancel each other out, so that from time to time, we get the majestic grandeur that is a total solar eclipse. And that's when the disk of the moon passes in front of the disk of the sun, and you perfectly block the disk of the sun. Here, the white fuzz that you see around the sun is an outer atmospheric layer called the corona. You'll learn about that later. But what's going on is the disk of the moon is ½ a degree, and it's perfectly covering the disk of the sun, resulting in a total solar eclipse. Sometimes eclipses can happen when the moon is a little bit farther away from the Earth at perigee, and that's kind of cool because you can get a very special type of an eclipse called an annular solar eclipse. During an annular solar eclipse, the disk of the moon will not perfectly cover the disk of the sun because it's a little smaller than ½ a degree. And you get this so-called ring of fire. You can see a ring of the sun around there. It's pretty wild, right? That's a very rare type of eclipse to see. We'll talk more about that next time. But if you think about it, on our nighttime sky, after the sun and after the moon, everything else is like a really small planet or star by comparison, right? So the angular sizes of stars and the angular sizes of planets, they're so microscopic that degrees are actually a really clumsy unit of angle for astronomers. Most astronomers never use degrees. And the last little module that I kind of need to do our homework today is just to tell you guys that there are 3 units of angle. We can come back to this later, okay? 3 units for angular size in astronomy. The first is the degree, which we've already been using. And 1 degree is 1/360th of a circle. Or in other words, we can write 1 circle contains 360 degrees. That's a kind of conversion factor, okay? We can then subdivide the degree into smaller increments called the arc minute and the arc second. And I expect that this is going to be somewhat new for you guys. Imagine taking a degree and imagine chopping that degree into 60 more little slices of pizza. So bump, 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 bump. There's like a 60th of a degree. That angle is called an arc minute, okay? So stop share. The second unit is called the arc minute. The abbreviation for an arc minute is a 1 with a single apostrophe. It's defined as a 60th of 1 degree. Or in other words, 1 degree contains 60 arc minutes. That's going to be our official conversion factor. 1 degree is equal to 60 arc minutes. We can make an even smaller unit of angle called the arc second. The abbreviation for an arc second is 1 double apostrophe. We define the arc second as a 60th of 1 arc minute. 1 arc minute, sorry, is equal to 60 arc seconds. That's right. I apologize for doing that module so quickly. We can talk about it at length in our next lecture, but we needed these 3 conversion factors for our homework today, so I felt duty bound to squeeze them in. Okay, get those notes down, and here's what I'm going to say. It's currently 1:08. I'm a little bit over. We're going to now start our homework module, which we're in a good place to do because I've covered everything that we need for our 5 homework questions. What I propose and what I usually like to do is between doing our lecture and homework, we take a little 5, sometimes even 10-minute break. I can drink some iced tea and we can just pause for a second before we start the next business. On the other hand, pausing stretches the day out. So what do you guys think? Are you cool with a little 5 to 10-minute break, or should you try to launch into it faster? What's the group say? I'm going to pause the.
I'd rather take like a 5.
5-minute break. All right, Fred likes the pause too. It turns out that
Yes,
once you start taking,
coffee.
yeah, have a little coffee. Let's take somewhere between a 5 or 10-minute break. I'm going to drink a glass of iced tea, Caitlin. I'll try not to doink around too much. I'll pause the recording so that the audience later doesn't watch any dead air. But please, folks, would you remind me to unpause the recording? Because sometimes I forget, and that's mischievous. Okay, so I'll see you guys in 5 to 10 minutes, close to 1:15, 1:20. All right. Sorry, someone wants to finish up the notes on the board, so I will pause it on the notes. Good call. Sorry, I paused it with my head in the way. Okay, I'm back and I'm ready for action. I just had to sit with the cat for a minute. So, shall we do our homework? Let me show you where you can get the questions, because I'm going to have some of you guys read them to me. If we go to our Blackboard page here, I'll just go to, all right, I'm in the 600 class, fine. So we go to the homework section, okay? And this is the homework we're going to be doing. We're going to handwrite it in our notebooks, and at the end, I'll help you guys submit it through this link here. But for now, if you just want to right-click and open up these 2 PDFs in a new tab, if you don't have the book, this will help us to sort of read the questions. Let's see here. This is chapter 1. This is the first one we need. And 42 is the first question that we're gonna tackle here. So, Caitlin, you're the first in my little box of humans. Caitlin, would you be down to read us question 42 when I ask you to?
Yes, of course. I have the book right in front of me. So
Oh yeah, and you've got the book. Cool. That makes you perfect for this. Let me show you how I want this set up, okay? Because I want us to all set things up in the same way. So at the top of the page on the left, obviously put your name. Then over here, I want you to put AS1020. And then after that, I want you to put whatever your section is. If you're in section 001, do that. If you're in section 102, the night class, then do that. If you're in section 600, then put 600. That's the online class. Remember, this always helps me figure out which section you're in, and that's important because I've got different boxes for different people. And then over here, we're going to write homework number 1 so that we can keep track of what we're submitting. And we're going to write down the questions. There's questions from chapter 1. There's questions from chapter 2. It looks to me like the assignment was, okay, whoops, chapter 1, 42 and 49. And from chapter 2, I have 53, 55, 58. So I wrote those down. Great way to format your homework. That way we know what we're doing, okay? And then keep it neat, keep it organized, no squishies. Chapter 1, 42. Caitlin, I'd like to hear the title of the question. What's the title called?
the title is called Scaling the Local Group of Galaxies.
By the way, a mistake that people have made in the past is just to wait till I do this whole problem and write down the answer. Wrong. You're supposed to do everything that I do on the board. I'm showing you how to do a problem set correctly. The problem is most people who are non-science students, they don't even know what you're supposed to do, how to make it look good. I am showing you how you do this with class and with style, all right? This is also going to be an excellent study tool come exam time. Caitlin, take it away.
All right, so scaling the local group of galaxies. Both the Milky Way galaxy and the Andromeda galaxy have a diameter of about 100,000 light years. The distance between the two galaxies is about 2.5 million light years. A, using a scale on which 1 centimeter represents 100,000 light years, draw a sketch showing both galaxies and the distance between them to scale.
All right,
B,
pause there. Pause there. Just hold on for a second. The distance between them is 2.5 million light years, but I think they wrote the word million out, right?
Yeah.
When I do a problem the first time around, I extract the givens, meaning I get the numerical information with units right out on the page. Pro tip. However, I want to put 2.5 million into number form. Million means we have to use scientific notation. Caitlin, how do I write 2.5 million light years? You're muted, buddy.
Wouldn't it be 2.5 times 10 to the 6th LY?
That's right. And that's exactly what we're going to write down. Beautiful. Okay. Now, we're about to solve problem A. And so label it A. In problem A, they've given us a scale factor. A scale factor will relate one set of units to a kind of scale model, kind of like if you have a map, 1 inch equals 10 miles or something like that. Okay. In this one, they said the scale factor we're going to use is 1 centimeter is equal to 100,000 light years on the page. I'm going to teach you guys an important tip here. I'm going to box my scale factor. A scale factor is a conversion factor that you make up. However, if you notice here on my meter stick, there's an actual number of centimeters in a meter. In 1 meter, there are 100 centimeters. and there are 1,000 meters in a kilometer, and there's 9 trillion kilometers in a light year. It is not actually true that 1 centimeter is equal to 1 light year, right? A light year is not the width of your pinky fingernail, right? That's not correct. Because of this, it can sometimes get confusing on whether or not you're talking about centimeters on the paper, on the scale model, or centimeters in outer space. So what I like to do is I like to use a prime to distinguish the scale model from the real units. So I put 1 centimeter prime, where this means fake centimeters, okay? Turns out that's a very smart thing to do. You're gonna have to trust me on it. All right. We know the distance between Milky Way and Andromeda is 2.5 million light years. We need to figure out how many fake centimeters that is on our paper. This sounds like a great opportunity for us to use one of the skills that I taught you in today's lecture. What's that skill called? What's the skill you use when you want to convert the whoas to the doodas? What do you do?
Would it be a unit conversion problem?
Yes, and the technique we use for unit conversion problems is?
It would be, well, the one that we did was about Pluto to the moon.
No, what's the technique called? Yes, Hannah, dimensional analysis, if I said Hannah right. Hannah says dimensional analysis. That's right. Okay. Okay. So Caitlin, since you're talking to me, although I'll get around to picking on everyone, don't you worry. Hannah, why don't you go back to your 4 steps of dimensional analysis? Let's read them out together. So what's your first step of dimensional analysis?
First one is write down the number to convert with its units.
Okay, yeah. Whoever's talking to me, yes, I love it. Could you just talk louder because you're quiet? Who's talking? I can't see.
It's me, Hene.
It's me. Wait, who's me?
Hene.
Oh, Hene. Hene,
Yeah.
is there a way you could turn up your volume a bit? If you go to in Zoom where it says mute, there's a little arrow next to mute. You can then go to your audio settings and you should be able to turn up or down your microphone. Check, check, check. Mine seems pretty good. You're just quiet as hell. And so it sounds like Hannah said the first, sorry, is it Hene?
Hene, yeah.
Hene says the first step is write down the number to convert with units. So Hene, what number are we trying to convert with its units?
Centimeters?
Hold on, can you say that again?
Is it light years?
How many of them?
Hold on, sorry, I'm like all over the place.
That's okay. Let's look at our question here. On a scale in which 1 centimeter is 100,000 light years. Well, here they kind of left it a bit abstract. Draw a sketch showing galaxies and the distance between them to scale, right? Okay, so I'll tell you what, why don't we start it this way? Let's start with our sketch. Now, I know that the answer is going to take up most of our page, and I actually want you to do this to scale. So the way that we draw a little galaxy is I want you to take a ruler and I want you to make a 1 centimeter line. Remember that a centimeter is pretty close to the width of your pinky fingernail. So I better see something like that on your page. And yes, I will fucking measure it. And yes, I will take points off if you don't do it right. Okay? So we'll make a line that's about 1 centimeter and make it diagonally up at the top near your name. That's a 1 centimeter line. And let me show you an art trick to make this like a galaxy. Put a bulge in the center and put some spiral arms, okay? So there's your galaxy, and it's 1 fake centimeter in scale. Or actually, it's 1 actual centimeter on the page. Now, part of the problem, Hene, is I need to figure out how far away to draw the next galaxy. So if this is the Milky Way, MW, I need to figure out how far away to make the Andromeda galaxy. And I know that the distance between them is 2.5 million light years. Do you understand what I'm saying, Hene?
Yeah.
So the first step in dimensional analysis is to write down the number you want to convert with its units. Why don't we start by writing down I'm down to give you guys the answers. I just want you to think about it and work with me a little bit, you know? Thoughts from the peanut gallery? Anyone? It's a group project here, guys. What the fuck do I do? That's what I'm asking.
I'm sorry, but I see that you.
Fred?
Can we just look at the question again, the A and B questions?
Yeah, but let's focus on A. We're having trouble remembering A, so I don't want to throw
All right,
B in there.
So
Okay.
the A one, because I don't think I wrote that down.
Sure. Well, you don't have to write it down because you can just right click on your Blackboard and open it up. You don't have to write down the whole question. Using a scale on which 1 centimeter represents 100,000 light years. In other words, we're making the diameter of each galaxy 1 light year. I'm sorry, making the diameter of each galaxy 1 centimeter. Draw a sketch showing both galaxies and the distance between them to scale. In other words, 1 centimeter is 100,000 light years. So the diameter of each galaxy is 1 fake centimeter. And we've drawn that. Now we need to make a line, and we have to know how many centimeters away the next galaxy would be to scale, correct?
You have to put down the light years.
All right,
No,
so
it'd be the opposite. Wouldn't it be centimeters? You would take light years and convert it into centimeters.
right, but then the first step is to write down the number you want to convert with its units. So the number you want to convert is 2.5 million light years. We're trying, in other words, we're trying to convert this and find out how many fake centimeters away the other galaxy is. Okay, Mikey, we got you, buddy, and we see you and we love you. And thanks for clarifying that, because I probably would have called on you. Let's start by writing down the number to convert with its units. We'll start by writing down 2.5 million light years. Okay, Hene, if you're still floating in the background there, what's the second step?
It's multiplied by a division bar.
That's easy. What's the third step?
Put the units in first to cancel.
Okay, so Hene, what units should I put top and bottom here?
You should put centimeters in the top and then light years in the bottom.
Yeah, but I'm going to do centimeters prime or fake centimeters because there is an actual conversion between centimeters and light years. We don't want to confuse those. Okay, what's step 4? By the way, make sure you cross out units. That was correct, Hene. Now, we can cancel out the light years.
And then you put the numbers in the second using conversion factor.
Hell yeah. So give me some numbers, person. Top and bottom. What do I got?
So you're gonna put 1 centimeter prime on top and then the 100,000 light years at the bottom.
Beautiful. Just like downtown, but closer. She's using her conversion factor, her scale factor. She's got the units, and so she keeps each number with its unit. It looks like what we're going to do is we're going to take 2.5 million. You don't really need to times by 1, but the fact that the 100,000 is on the bottom basically means we're going to divide. That's on the top, that's on the bottom, so this is a division, right? So what we do is we take our calculus.
My calculator is downstairs. Do you mind if I go get it?
Go grab it. Go grab it. We'll try to go slow. Okay, so we do 2.5 EXP6, that's 2.5 million, divide by 100,000. Oh, okay, I clearly fucked up somehow, sorry. Let me try that again. 2.5 EXP6 divide by 100,000. Looks like our answer is 25. And what are the units?
Fake centimeters.
Good. We've just earned ourselves 1 point. Each homework problem is based out of 5 points. That was one of the points. Now, for 2 more points, getting the diameters of the galaxies correct is each a point. or as 1 point. Now we're going to make a line that is 25 centimeters long. It's going to take up most of your page if you're using a standard 8.5 by 11. So, so that you guys could see, I actually made mine 10 centimeters, sorry. So 25 times that. I don't think I can actually do that. Okay, so I'm cheating a little bit, but on your page, you shouldn't cheat. You should use a real ruler. You should actually make it 25 centimeters. It should go all the way down to the bottom of your page. And then at the bottom of your page, make another 1 centimeter line in the middle. Just like I did, all right? And then draw in your bulge and draw in some spiral arms. We'll make barred spiral galaxies, okay? Somebody's running the garbage disposal back there. Who are you? Let's show non-video participants. Who's running their garbage disposal? Oh, you hid yourself. Very good. Very clever of you. Okay. There we go. And now we've earned 3 points. We've completed part A. Please use an actual ruler and make it 25 centimeters. I know what 25 centimeters is. I'm going to know if you've been cheating. Okay. All right. Fred's got a ruler. I'm happy. Go ahead and read me part B when you're ready, Caitlin.
Sorry, I was doing my measurements because I'm using a measuring tape.
Yeah, by the way, if you do not have a ruler, because you didn't listen to me, 25 centimeters actually happens to be just about the length of your book. Your book is actually 26 centimeters long. So you could use the edge of your textbook, and that would be a pretty good cheat.
All right, so question B. How does the separation between the galaxies compare to the separation between the stars?
Well, Caitlin, this is a very complex question, part B. I want to do just that piece of it for starters. How does the separation between galaxies compare to the separation between stars? So remember that galaxies are typically separated by a distance of like 2 to 3 million light years. Whereas stars, what did we say was the typical separation between stars? In our lecture today.
Is it 4.4 light years?
Let's just say 4 light years, keep it simple, okay? So it's about 3 million light years between galaxies, 4 light years between stars. So I think it's pretty safe for us to say, let's play an old astronomer's trick. Let's say 4 is approximately equal to 2.5, okay? And if that's true, then we could say the separation between galaxies hold on, I got to get my tense correct here. The separations between galaxies are literally millions of times greater than the separations between stars. So that's the first. Part B is a 2-part question. And I wanted to start by answering the first part of it. The separations between galaxies are millions of times greater than the separations between stars. full stop. Okay, Caitlin?
All right. Based on your answer, discuss the likelihood of galactic collisions in comparison to the likelihood of stellar collisions.
In other words, what they're saying there is, what is more likely to collide with each other, stars or galaxies? Class?
Stars.
That's what it would seem to be implying. And this would be a good example of why you don't want to do the homework by yourself. They are tricking you. They are being tricksy, false hobbitses, okay? In fact, there's a sort of sleight of hand going on here that you should be wary of. You will notice that in part A, they asked us to draw a scale model where a typical galaxy was about 1 centimeter in diameter. And we discovered that relative to the diameters of galaxies, if we make the diameter a number 1, that galaxies are separated by about 25 times their diameter, correct? If they were really wanting us to learn this problem right, why didn't they ask us to do part A for stars? Now, we are more badass than the average astronomy bear, and we are going to do that. That's what I demand of you in return for free answers to your homework. So I need to erase here for a second so that we can do part B proper. Here I go. I'm erasing.
Actually, I got a question about this.
Yeah.
Because the way that the problem sounds to me, and I'm maybe misunderstanding the concept here, is that are they trying to say what the distances between the edge of these two galaxies are? Like, so for instance, 25, if each one of these is 1 centimeter, then the diameter would be like half a centimeter. So there would be basically 24 centimeters between them.
Here, what you need to understand is that astronomy is a low precision science. And this is going to be unnerving for you guys for a little bit, but once you get in the kooky cowboy logic of it, you're going to start to love it. Remember, Fred, that just a few moments ago, I made a very astronomy analogy or approximation where I said 2.5 is approximately equal to 4, and nobody batted an eye, right? So while I understand what you're saying, Fred, I want you to look at it this way. Here's a couple of marbles, okay, that are about 1 centimeter in diameter. Where's my the GD meter stick here? Here it is. While what you said is important, Fred, remember that compared to these separations, if it's a 1 to 25 ratio, the separations between the galaxies, it kind of doesn't, trying to get this in the picture here, it kind of doesn't matter whether you measure from the center of the galaxy or the edge of the galaxy, because the entire diameter of the galaxy is a small fraction of the overall thing. So it's almost like, who cares? Measure from the edge, measure from the center, measure 3/4. Now, if we were talking about the distance between the Milky Way and the Large Magellanic Cloud, one of the orbiting galaxies, then you'd have to ask those questions. But when it's 100,000 versus 3 million, at a 1 to 25 ratio, you can sort of start to not worry about those questions. So I understand why you worried about it, but I'm telling you here, you don't need to. And that's an art form that you will just have to learn over time, okay? Keep asking them good questions. I want to erase, and let's try part B for stars. Now, I didn't get to make my sort of analogy here, but let's go off-roading for a second. Let's just go off-roading. I don't do this too often, but when I do, it's for a damned good reason. So for part B, let's just say that I know that the radius of the sun is 700,000 kilometers. And that means that the diameter of the sun is 1.4 million kilometers. Now, I want you to imagine that I played the same kind of game with the sun that I did with galaxies. Imagine I have a star, and imagine that the diameter of the star, what if I pegged the diameter of the star to be 1 centimeter? And what if instead I wanted to come up with a new scale factor where 1 centimeter was equal to 1 million to 2 million kilometers? And I'm trying to ask the question, if this is the sun, how far would I have to go to get to Alpha Centauri on that scale? Where I've used the Greek letter alpha for Alpha Centauri. We know that the distance between these two things is about 4.4 light years. I'm going to show you a more advanced trick with dimensional analysis. I cannot easily convert light years into fake centimeters. Why? Because I don't have a conversion between light years and fake centimeters. I did in the previous problem, but that's when we defined the diameter of a galaxy to be 1. Here we're saying, what if we had done the same thing, but now 1 centimeter was the diameter of the sun, right? I'd have to do a 2-step dimensional analysis. First, to convert light years to kilometers, because I know that conversion, and then to convert real kilometers to fake centimeters. And to do a 2-step dimensional analysis, you can actually multiply by 2 division bars, or you can think of it as doing step 2 twice. Now, I want you to watch my methods here. Units come in first and numbers come in second. Light years on the bottom will cancel light years. And I'm first going to convert to kilometers. I know the number of kilometers in a light year because I gave it to you in class today. Then I'll do a second step where I convert kilometers to fake centimeters using that conversion factor. So I'm doing this a little quicker than I normally would do, but that's because I want to try to keep our homework times to a minimum. I'm going to ask you guys to do the last part. Can you go into your lecture notes for today? Can you find that conversion factor and that conversion factor and help me put the numbers in?
What's the 4.4 light year from?
I taught you in today's lecture that the distance from Earth to Alpha Centauri, the nearest star, was 4.4 light years. So I'm taking 4.4 light years as a typical separation between stars. Just like I'm taking the distance between Milky Way and Andromeda to be a typical separation between galaxies. In other words, somebody told you that. Class, help me with this conversion. I probably should have left a little more room there. Let me increase the length of this here.
So
anyone?
yeah, so you're gonna put 1.4 times 10 to the 6 km on the top line.
Which top line?
The first one, the km on the top.
Sorry, the first fraction bar is a conversion between kilometers and light years.
Okay.
That's the conversion to centimeters. Go into your notes to find the conversion between light years to kilometers.
So do you put the 9.5 times 10 to the 12th on top?
That's right. In today's lecture, we learned that there are 9.5 times 10 to the 12, or 9.5 trillion kilometers in 1 light year. So we put 1 light year on the bottom. Nicely done. How about over here?
So you put the diameter of the sun on the bottom and then 1 centimeter on top.
That's right. So 1 goes with the centimeters and 1.4 million goes on the bottom. Basically, what we're going to do is we're going to do 4.4 times 9.5 trillion divided by 1.6 million. Let's go ahead and do that now. Not everyone's got their Casio, so I'll punch along with you. But in general, I want you guys to do the punching, okay? 4.4 times 9.5 exp12 divide by 1.4 exp6 equals. Okay, now let's think about how we want to round this. The decimal point is right there between the 2 and the 8. I want to round this really hard. Let's just round our lead digit to 3. What would the answer be in scientific notation? Last time I couldn't get the camera to focus far away. Now I can't get it to, I still don't have good control over this thing.
3 times 10 to the 7th.
Yes, you could do 3 times 10 to the 7th. That would be perfectly valid. But I'm not gonna trick you. I'm just gonna do it a little differently. For my own personal taste purposes, I'm gonna do 30 times 10 to the 6 fake centimeters. Because I want to think of it as 30 million fake centimeters. Does anyone understand why they did not ask us to do part A for stars?
So we wouldn't have to do 2 conversions.
No. Was that so bad?
No, that's why I sounded confused when I said it.
I don't think you guys understand what 30 million centimeters is. I know that there's 100 centimeters to a meter, right? So if I converted that from fake centimeters to fake meters, 1 meter is 100 centimeters. So that would be divide by 2 zeros, 10 to the 5, 10 to the 4. Wait. 10 to the 5. That would be 300,000 fake meters. And if I converted that to fake kilometers, that would be 300 fake kilometers, right? I think 300 kilometers is like the distance between here and Bangor, Maine. I'm not really sure. What's 300? I'm not really good always in working in kilometers. Providence, Rhode Island to Portland, Maine. It's 163 miles. Yeah, okay. You would need, the reason why they didn't ask you to do part A for stars is if you made the diameter of the sun, this ball bearing here is about 1 centimeter, right? If you made the diameter of the sun 1 centimeter, the nearest star, you'd have to have a piece of paper the size of New England to put the next star on it. Class, what's farther apart? Stars or galaxies?
Stars.
No fucking way.
Galaxy.
Galaxies are millions of light years apart. Sorry, yeah, millions of light years apart. Stars are of order 5 light years apart. But what do you think is more likely to collide, stars or galaxies?
Galaxies.
Stars.
That's right. And it's because it's not just about how far away you are, it's about how big your target of cross-section of collision is, right? In other words, if you compare galaxies to stars, galaxies have a distance to diameter ratio of 25 to 1. But stars they have a distance to diameter ratio of 30 million to 1. And because of this, the stars almost never collide because their diameters are so small and relative to their separations that it's almost impossible to get them to bump into each other. On the other hand, I cannot show you a single astro photograph of a star collision. We don't have a picture of two stars colliding, but I can show you thousands of pictures of galaxy collisions. Like, for instance, one of my favorites is Stefan's quintet, which is like a big galaxy pileup. And if you look over here, let's try this picture. Actually, I don't think all these are exactly the same distance, but do you see this thing over here? These two are two spiral galaxies that are sort of smashing into one another and sharing gas and stars.
Looks like something out of Mass Effect.
Yeah, it's so cool, right? Another legendary one is the antennae.
Before we move off of this one,
yeah,
going back to the 25 centimeter drawing that we did between the galaxies. So would the distance between the stars be the 25, and then the galaxies that 24?
No, Fred. I think you're getting confused. Galaxy diameters are relative to their separation by 25 to 1. Galaxies are 25 times farther apart than they are to size. But stars are 30 million times farther apart than their diameters.
I understand that, but so then I don't understand the drawing we did between the stars and their galaxies in the 25 centimeters.
Well, we didn't really draw the two stars separated to scale. I started to draw it to get you thinking about it, but this isn't to scale. This is fucked up, right? This is actually more like a galaxy to diameter separation. I left the question mark there to show you that ... You'd have to keep going, right? In other words, this isn't the real picture. We couldn't draw the real picture. That's why they didn't ask you to do it. But the one that we drew in part A was accurate for galaxies. That was correct. It doesn't matter if you measure from the center or the edge. It's not important. Let me help you write out what the last part of part B is, okay? The answer should flow like this. However, the distance to diameter ratios for stars are, if you say 25 is approximately equal to 30, which I think is fair, the distance to diameter ratios for stars are actually millions of times greater than galaxies. So galaxies are much more likely to collide. And that was the sort of gotcha or the aha moment there. It's about distance to diameter ratios.
Does speed also play a factor in that?
Well, in a weird way, no. And the speeds of these things are governed by orbital dynamics. For instance, the speed of stars, the stars are traveling at hundreds of kilometers per second around the galaxy. But because Earth and Alpha Centauri are in the same part of the spiral arm of galaxies, they're kind of sweeping along in the river together, and they only move at a few kilometers per second relative to each other. The reason why speed doesn't matter is because astronomers think in terms of really long time scales. We want to know, would stars collide over the hundreds of millions of years it takes to go around the galaxy's center? You know what I mean? Okay, Fred, well, can you come back and watch the rest of this video later? I promise not all the questions will take this long. This one was a bit of a whopper. And actually on that note, I'm not going to get into the speed thing because it's going to be hard to explain. The answer is no. And I don't want to spend another 20 minutes explaining it. Let's move on to the next question, okay? I'm going to erase. Does everyone have this? Fred, we love you. By the way, as I go through the videos, I tend to slash out problems. That should help you scrub and figure out where we are in the recording. All right, I'm going to erase. Okay, let's ask someone else to read. Vincent, you're the next person in line. Would you be down to read chapter 149 for me? Appreciate it.
Sure. Universal scale. Suppose we wanted to make a scale model of the local group of galaxies in which the Milky Way galaxy was the size of a marble, about 1 centimeter in diameter. Part A. How far from the Milky Way galaxy would the Andromeda galaxy be on this scale?
This is basically the same question that we did in the previous problem. There's a reason why I asked this question next. I wanted us to just do some faster conversions, okay? So once again, we've got 1 centimeter is 100,000 light years. And in A, we want to do the Milky Way galaxy to the Andromeda galaxy. We know the distance between them is 2.5 million light years. So let's just quickly bang this one out so that we can move along here. We're going to start with 2.5 million light years. We're going to multiply by a division bar. We're going to put light years on bottom and fake centimeters on top. We're going to use our scale factor, and we're going to do 1 fake centimeter is 100,000 light years. We're going to punch them up, and if you remember in the last problem, we got 25 fake centimeters. I did that one quickly because we already kind of did that, all right? Vincent, once you've written that down, give me part B.
Part B. How far would the sun be from Alpha Centauri on this scale?
Okay, this is a little bit different than what we just did, because in the previous problem, I set the diameter of the sun to 1 centimeter. But here, they're going to maintain the same conversion factor. They're going to say, if you still have the size of the Milky Way as a centimeter, if a centimeter is equal to 100,000 light years, then how far would the distance be from the sun to Alpha Centauri? So we know the distance from the sun to Alpha Centauri is 4.4 light years. What do we do next? Let's do dimension. Vincent, you start me off here. I want to do dimensional analysis. What's the first step in dimensional analysis?
First step is write down the number to convert with its units.
So what should I write down?
You should write down, you want to convert from the light years to the centimeters.
How many light years?
4.4 light years.
So that's what we write down. We start by writing down 4.4 light years. What's step 2?
Multiply by division bar.
That's what I'm going to do. What's step 3?
Put the units in first to cancel out.
All right, so give me them units.
So you want to put light years on the bottom and fake centimeters on top.
Beautiful. And step 4?
Put the numbers in.
Yeah, Vincent, don't forget to cancel out light years, top and bottom. That reminds us why we did that. Okay, so help me put the numbers in.
So you would put 1 fake centimeter on the top, and then 100,000 light years on the bottom.
All right, you're pretty good at this. I like you. Okay, so want to punch that up for me, guys? Who's got a Calci? We'll do, let's see here, just trying to make it 4.4. I don't need to multiply by 1. That's pointless. I'm going to divide by 100,000. Looks like I got, how do I write that down on my page, class?
It would be 4.4 times 10 to the negative 5th power.
And what are the units?
Fake centimeters.
Excellent. Put a box around it because that's a classy move. Part C. When you're ready, Vincent, finish writing and then read.
Part C. How far would it be from the Milky Way galaxy to the most distant galaxies in the observable universe on the scale?
In other words, Milky Way to the edge of what we call the observable universe. Now, most of you guys are thinking, I don't know what the shit the edge of the observable universe is. Fine, that's fair. But let me explain that the way we're supposed to think about this is it's about, let's just type in observable universe. The concept of the observable universe is not super hard to understand. At least I don't think so. The idea is if you're in the Milky Way and you're here, okay, in the center, you can only see as far out into space as light has had time to reach you from some distant galaxy. So if I'm a galaxy here, okay, here's my galaxy, it's emitting photons, and it takes time for those photons to reach us. Now, I know, because I'm an astronomer, that the age of the universe is about 13.6 billion years old. You can actually type in age of universe into Google, and it'll tell you it's about 13.8 billion years old. That means if light travels 1 light year per year, I should not be able to see any galaxies that are farther away than 13.8 billion light years because light hasn't had enough time to reach us. That's what's called our observable universe. There can be galaxies outside of that sphere, but you won't be able to see them until next year, okay? So let's take as our distance 13.8. How do we do billion again? 10 to the what?
9.
9. So we'll do 10 to the 9 light years. And now we're going to do a conversion on that scale. So Vincent was really awesome how he set this up. Let's walk us through it again. So we'll do 13.8 billion light years. We'll put down our division bar, light years on the bottom, fake centimeters on top. We cancel out light years. We slap in our conversion factor. 1 centimeter, 1 fake centimeter is 100,000 light years. And we divide. Sorry, I'm trying to find a good spot here. 0.8 exp9 divide by 100,000. 138,000 fake centimeters. And that basically takes care of our second question, 49. So we'll try to pick up the pace a bit here because I diddled around on the first one. Let's do 12. All right. Remember, students, either we're doing this together or you're doing this on your own. And I don't think you want to be doing this on your own, right? All right, Mikey says hell no. All right.
No.
Can I erase? All right. Chapter 2, number 53. David, how do you feel about reading?
No problem. Give me 1 second.
You'll have to go to the other PDF now.
What was it, 49? Oh, 53, sorry. About arc minutes and arc seconds?
Yeah, this one's also easy.
Okay. Arc minutes and arc seconds. There are 360 degrees in a full circle. A, how many arc minutes are in a full circle?
All right, let's just pause there. So one circle equals 360 degrees. That's what they started us off with. Part A. How many arc minutes? David, is it obvious to you how to start this thing up?
One second. So if one circle equals 360 degrees, are we again using the
Dimensional analysis, yes, that's the technique always. David, if you're feeling a little overwhelmed, just read off the steps of dimensional analysis, and that's going to help us.
So we're gonna write
Anyway,
write numbers to convert with its units.
so what number am I trying to convert with its units?
Degrees to arc minutes.
Yeah, but how many degrees?
360.
Right. So we start by writing down 360 degrees. What's the second step?
The division bar multiplied by division bar.
What's the third step?
Write out the units.
All right, give me some units, top and bottom.
So the bottom, I believe, will be degrees.
Yep.
And then the top will be arc minutes.
Yeah, remember that the symbol for arc minute is a single apostrophe. Don't forget to slash out your degrees. Fourth step.
We put in the numbers.
Okay, Mikey, yeah, please finish the video later. Sorry I wasn't more expedient about this. I'll try to be better in the future. We need a conversion from degrees to arc minutes.
So you would put 360 at the bottom?
Hold on. What's your conversion factor? Let's put that over here on the side. What's the conversion factor? From today's lecture, last bit of notes.
1 degree to 60 arc minutes.
That's right. This is the conversion factor that we need to be using. Notice that there is no 360 there at all. So someone try again.
So 60 would go on top and one would go at the bottom.
Beautiful. All right, punch them up. 360 times 60, what do you get?
$21,600.
Units?
Arc minutes.
Good. So put that apostrophe in, box it. That's a classy move. Part B.
So want me to read it?
Sure. Yeah, you're the reader for this question.
Part B, how many arc seconds are in a full circle?
Okay, there's a couple of different ways we could do this. How do you guys want to proceed?
The simplest way.
All right, what is that way? Simple to you and simple to me are always the same thing.
Would you do the dimension analysis for it?
Always. That goes without saying. We always do dimensional analysis. I just want to know what to do. What do I start with, in other words? What's step one?
60 degrees.
Pardon?
360 degrees.
All right, we can start there. That's fine. Now, we can't go directly from degrees to arc seconds because we do not have that conversion. So what are we going to do about that?
I believe we're going to be converting twice.
That's right. So the first time we'll do degrees to arc minutes, and the second time we'll do what?
Arc minutes, arc seconds.
That's right. And what's our conversion from arc minutes to arc seconds?
1 equal 1. Oh.
1 arc minute
One arc. Never mind.
I'm with you guys. Just got to finish the stroke there.
1 arc minute, 60th arc second.
Right. Okay, so help me put the numbers in, guys. What are the numbers?
$60 on top and 1 on the bottom for both of them.
Excellent. Okay, punch them up. Tell me what you get. We could have also started with 21,600. I was going to see how you did it. That number is bigger than a million, so put it in scientific notation for me. Come on, guys. I don't want to grow old and die here.
Would it be 1.2 times 10 to the 6th?
All right, first of all, that's shit rounding. If you're rounding to 2 sig figs, you can't keep it 1.2 if there's a 9 afterwards.
1.3 times 10 to the 6th arc seconds.
Now, Caitlin, yes, 1.3 would be fine, but since we're doing this together, I'd like to point out to you guys that there is a perfect 60 arc minutes in 1 degree. There is a perfect number of 60 arc seconds in 1 arc minute. So here, if we wanted to keep all of that precision, we weirdly could, because there's no rounding errors. If you define exactly 60 arc minutes in 1 degree, then there's no measurement precision associated with that. So to demonstrate this, I'm going to actually leave it 1.296 million arc seconds. And yeah, you could have made it 1.3. I would have accepted that. But here I'm letting you know that you can actually keep all of those digits of precision. Okay, part C.
The moon's angular size is that half a degree? What is this in arc minutes and in arc seconds?
All right, let's see if we can bang this out really fast. What do I do? Get my stool here.
Wouldn't your starting conversion be your starting number be half a degree?
Correct. Division bar. Units.
Reason arc minute
Yep. What's the conversion?
would be 60 on top, 1 on the bottom.
Good. Punch it up. What's the answer?
It's 30 arc minutes.
Good.
And then you would do, for arc seconds, you would do, yeah, you would do it times 60 arc seconds over 1 arc minute.
And what do you get if you do that?
1,800 arc seconds.
Nice. Box those two up. Classy. 53 is down. We're moving quick now, and I like it. Sometimes I spend a little more time on one problem and a little faster on the others. I try to keep the homeworks to within an hour and a half. As you guys get stronger and better, we will get faster at the homeworks. The first couple of weeks will be a little rough. Emma, are you cool with reading the next problem for me?
Yeah, just. Oh,
Let
damn it,
me,
sorry, I got signed out of my Blackboard. Hang on 1 second.
Oh, that's okay. Hey, can I erase this, or does anyone still need to copy? Chapter 2.
Chapter 2, and this is 55.
Yeah. Before you start reading, Emma, it might be good for me to qualify here. First of all, let me see how we're doing with folks here, because I've got 4 sharing video. Thank you very much. What am I doing with trolls here? Okay, it looks like I've got a whole bunch of trolls. 1, 2, 3, 4, 5, sorry, 8 trolls. Okay, so people are still appreciating the live thing. That's what I want to make sure of. Okay, hide non-video participants. All right. Before Emma reads the next question, I want to help you understand. Someone just chatted me here. What is that? Oh, that's okay. Amanda, pop back in. Hey, Amanda, if you're just joining us, let me explain what's going on. We are midway through the homework. We just did these 3 questions, so you're going to have to go back to watch those, but you can at least follow along with these last 2, which I think will help. Now, for those of us who are about to do question 55, I want to explain what's going on here. If you go and look up a star on Wikipedia, like let's look up the legendary star Betelgeuse, which will be in our next final problem. When they give you the coordinates of a star, we're going to be doing coordinates next week. You'll notice that they often list the coordinates of a star, its position on the sky, in terms of an angle, and they format it in the following way. Let me control plus this here. Notice that when they list the coordinates of Betelgeuse here, its so-called declination, you'll see them listed as +7 degrees, 24 minutes of arc, and 25 arc seconds and change. And that's actually quite similar to how we also do latitudes and longitudes. For instance, if you guys are rocking an iPhone, you can go to your compass app, okay? So somewhere on my app here, I've got compass, okay? And they give you your coordinates. The contrast might be an issue here. Fuck, it's the, okay, so this is all blurred out for the audience, but if you do this on your own iPhone, my latitude and longitude are listed as 41 degrees, 49 arc minutes, and 23 arc seconds. It's kind of similar to how we do timestamps on YouTube, right? We don't say 1.29675 hours. We do 1 hour, 30 minutes, and 24 seconds. That's the format that we're looking for here. So with that in mind, Emma, take us away.
Okay.
What's the title?
Angular conversions 1. The following angles are given in degrees and fractions of degrees. Rewrite them in degrees, arc minutes, and seconds.
So we are
in arc seconds, sorry.
We're going to go from degrees to this format. Some number of degrees, some number of arc minutes, some number of arc seconds. This is the format that we're looking for. All right, give us our first one in part A.
And our first one is 24.3 degrees.
Okay, let's think about our format here. We already know the whole number of degrees. That's 24. Our goal is to figure out how many arc minutes and how many arc seconds. Emma, any thoughts about how I might start that operation?
Yeah, you start by multiplying 24.3 degrees.
Careful, buddy. Listen, if you do that, you're going to find the number of arc minutes in 24.3 degrees. But we've already kept the 24 as a whole number of degrees. It's the fractional degree that we want to convert to arc minutes and arc seconds, right?
Okay.
Did that make any sense, what I just said, or was that confusing?
So is it just the 0.3 that we want to convert?
That's right. We have to take the remainder, 0.3 degrees. That was tricky. And now we'll make a division bar. Give me some units, bud.
At the top, you're going to have arc minutes, and at the bottom, you're going to have degrees.
Correctamundo. Cancel degrees. Give me the conversion factor.
At the top, you're going to have 60. At the bottom, it's going to be 1.
Beautiful. And then what do? What's 6 times 3?
18.
And then this is 10, but that's 1/10. They cancel out. So that's
so 1.8.
No, it's actually.
Or sorry.
If it was 0.3 times 6, it would be 1.8.
Oh, right. Sorry.
That's okay. Punch it in. We really should just punch into our calculators, but I'm also helping us think. So if it's 18 whole arc minutes, there's no remainder to the arc minutes. So what should my arc seconds be?
Is it 0?
18.
Yeah. And let's use what we call cell padding. I want to have 2 digits for each. So I'll do 0, 0 arc seconds. Just, you know, like we were working in Microsoft Excel, we'll use cell padding. Okay, B.
Okay. B is 1.59 degrees.
Okay. So we know our format. We have 01 degrees. Sorry about my 1. All right. Okay. And now we got to figure out the arc minutes and the arc seconds. So what do? Second verse, same as the first.
You multiply 59 degrees with arc minutes on the top and degrees on the bottom.
Punch it into your calci for me. At this point, like you guys do the punching. I guess not everyone's.
35.4.
Okay. And the units?
Arc minutes.
So we can take the 35 and plug it into the box for arc minutes, right?
Right.
So now
and then you take the 0.4 arc minutes and convert it to arc seconds.
And what's the conversion factor there?
At the top, you're going to have arc seconds, and at the bottom, arc minutes, and it's 60 at the top and 1 at the bottom.
Now, can you do it in your head the way we did it before, Amanda? 6 times 4 is equal to?
24.
And then the 10 cancels with the 1/10.
So it'd just be 24.
Yeah. Or punch it in your calculator if you can't do it in your head. That's fine too. All right. We got a few more parts, so let's do them quick.
Okay.
I hope I left that up long enough. Sorry. If not, go back, pause the video. Part C.
C is 0.1 degrees.
Okay. So it looks like we don't have any whole numbers of degrees. So I'll do 0, 0 degrees. Let's do our 0.1 degrees. Degrees to arc minutes. 60 to 1, what do you get?
6.
And so 0600. Bam, we're done. D.
Sorry, I'm just finishing right
Yeah, write first before you read. That'll give everyone some time. So what I'm trying to demonstrate is I can go quite fast in these, but I don't want to go so fast that I burn you guys, you know?
I was like,
Nah, I'm just gonna say my bad. I'm not on the camera. I'm just going through it, writing all this down.
Well, guys, this has to be like a bit of feedback and give and take, right? So if I'm going too slow, I know it's hard for anyone to say that. If I'm going too fast, you should definitely say, hey, give me a second to finish. And that's okay.
Nah, it's okay. I'm just getting accustomed to like all the math and all the crazy stuff that I'm seeing. It's like
it's gonna seem crazy at first, Lionel. If that is that Lionel that I hear back there?
Yeah, that's me.
Lionel, just stay cool under pressure. This might seem crazy at first, but it's actually by a week or two, you're just going to be not even thinking about it. It's going to be second nature. But the way to get comfortable with it is just practice, practice, and more practice.
okay. Should I read it now or?
Yeah.
Okay. So D is 0.01 degrees.
Okay. So there's no whole number of degrees. Let's convert the fractional degree to arc minutes. 60 to 1. Emma, can you do this one in your head?
0.6.
Yeah, because It's
arc
a
minutes.
hundredth versus a tenth, right?
Yeah.
If you don't believe us, punch it in your calc. That means there's no whole number of arcs minutes. And now we'll convert from arc minutes to arc seconds. Also 60 to 1. 6 times 6 is 36. So I think that's what it's going to be, right? Yeah. Lastly, we'll do part E.
Okay, and for part E, it's a 0.001 degrees.
Okay, that means just like the last one, you're not going to have any whole numbers of degrees or arc minutes. So let's just do this 0.001 degrees. Let's convert right from degrees all the way to arc seconds. Oops, sorry. Degrees cancel with degrees to give you arc minutes. Arc minutes cancel with arc minutes to give you arc seconds. 60 to 1, 60 to 1. And I'm pretty sure that's going to give you 3.6. We'll just leave the fractional arc second in there because that's how they did it for Betelgeuse. That means we've completed our fourth question. One more to go. Okay. Are you done cooking? Someone's cooking and it smells good. I think that's also motivating me to move fast. Green curry. Ooh, I love teaching from home. All right, let's move forward. That green curry isn't going to eat itself, you know? All right. I'm erasing. All righty then. Chapter 258. Wait, what am I doing here? Let's get rid of all this. This is the final whopper. Caitlin, we're back to you because I've only got 4 people here.
All right, so it's called Betelgeuse diameter. And the first part is estimate the diameter of the supergiant star Betelgeuse from its angular diameter of 0.05 arc seconds and the distance of about 600 light years. Compare your answer to the size of our sun and the Earth's sun distance.
All right, let's first draw the picture that we've got going on here. It's similar to the picture that I drew for you guys earlier today. We've got a star, which is spherical. Sorry, my tape kind of sucks here, or my drawing skills suck. Okay, so there's my star. I'm going to try this one more time, guys. Right? And the star has, sorry, my givens are getting distracting here, so. 0.05 arc seconds, 600 light years, okay? This is the star's diameter. We're observing it from Earth. Now, Fred, if you're watching later, it doesn't matter if it's 600 light years from the sun or Earth because it's such a bigger distance. So here's you, you're the observer. And we know that the distance is 600 light years away. Here, the angular size is 0.05 arc seconds. We want to find the diameter of the star. This looks like a job for what formula that you learned about today?
Dimensional analysis.
Well, dimensional analysis is for unit conversions, but here we actually need a formula.
It's gonna be a small angle formula.
Yeah, we got to use the small angle formula, which says that the size of Betelgeuse is its angular size times the distance times 2 pi over 360 degrees. But here we've got an issue, okay? Let's talk about our issues for a second. Issues that prevent us from solving the problem are that in our sample problem in class, theta needs to be in degrees. And while it's not strictly necessary, it's probably a good idea for the distance to be in kilometers. But our distance is currently in light years, and our angular size is currently in arc seconds. That means we got to do what?
Convert.
Yeah. So let's start by, let's convert the angle to degrees. We're going to start with 0.05 arc seconds. What do I do next?
You would put it back into arc minutes.
So
It would be 1 arc minute.
units first, numbers second, Caitlin.
So do arc minutes on the arc minutes on the top. No, arc seconds on the top. My bad. I'm getting myself confused. Sorry. And then arc minutes on the bottom.
I'm a little concerned because arc minutes are on the top here, and arc seconds are on the top, and arc seconds are on the top. If I multiply arc seconds by arc seconds, I get arc seconds squared per arc.
Then flip them.
Yeah, that's why we wait and we do the numbers second. The units have to get balanced first. All right, now your arc seconds will cancel. Now you can give me the numbers.
It would be 1 arc minute over 60 arc seconds.
Good. Now let's go ahead and do the next division bar because we have to get to degrees. What units should I do in the next spot?
So you would have to cancel that out again. So it would be degrees on the top, and then arc minute on the bottom.
Correct. And now let's put in that conversion vector.
And that would be 1 degree to 60 arc minutes.
Okay. So why don't you guys take 0.05 divided by 60 divided by 60. Not everyone's got a calculator the first day, so in the future, I want you guys punching. That's your job, not my job, but I'm helping today because not everyone's got their shit together. So 0.05 divide by 60 because it's on the bottom, and divide by 60 again. So how should we round that? Oh, cool, Caitlin. Oh, I saw that just now.
Yeah. Wouldn't it be 1.4 times 10 to the negative 5th power,
That's right.
and that would be degrees.
Yeah, don't make it look like -50. Make sure you're careful with your notation there. All right. So there's our angle. Let's work on converting 600 light years to kilometers. Sorry, guys, I'm going to have to erase here. So hopefully you got this first part down. Let's now convert the distance to kilometers. So we'll start with 600 light years. Do a division bar. Give me my units.
Would light years be at the bottom and kilometers be on top?
Beautiful. Thank you. And now someone, I need you to look up that conversion factor for me.
(9.5 times 10 to the 12 kilometers, sorry, over 1 light year.
Okay, I wanted to make sure you knew that it was on the top. That's right. All right, punch that up for me. (600 times 9.5 trillion EXP12). (5.7 times 10 to the 15 kilometers). Okay, now that we have our distance in kilometer and our angle in degrees, you don't really need to box these because these are intermediate, but I'm doing it anyways. Now it's time to do what the kids call plug and chug. That means we plug in our numbers and we get an answer, okay? So the size of Betelgeuse will be the angular size, 1.4 times 10 to the negative 5 degrees. I want to see all of this on your paper, kids, times 5.7 times 10 to the 15 kilometers times 2 times pi over 360. This probably seems wild to you guys, but it's not really a big deal once you get used to scientific notation and punches. This is basically punching 5 numbers, you know? 1, 2, 3, 4, 5. Easy. All right, so let's do it together. So we got 1.4 EXP negative 5, that's the angle, times 5.7 EXP 15, that's the distance, times 2. Remember that if we hit times first, we can just hit the EXP key. That's times pi. And now we divide by 360. We hit equals. That's the correct answer. Your job is to help me round it and put it into scientific notation because that's obviously bigger than 1 million. 2 sig figs will do for me. What you got?
1.4 times 10 to the 9th.
Units?
It's in kilometers, isn't it? Or is it light years? No, it's kilometers.
It's kilometers. If you look at your inputs, right? This is your input and that's your output. Degrees on top, dimensional analysis keeps working even when you're doing formulas. Degrees on top cancel degrees on bottom. The only units left are kilometers because those numbers don't have units associated with them. The diameter of Betelgeuse is 1.4 billion kilometers. At this point, we're almost done. You've got 4 out of 5 points. But I'd like to remind you that they asked us to compare our final answer. First, to the diameter of the sun. Secondly, to compare it to 1 AU, the distance between Earth and the sun. And in our class, I want to explain what compare means. When you compare things in astronomy, when you compare numbers of wildly different orders of magnitude, compare means take the ratio. Let's write that down. Compare means you take the ratio. We want to compare to both the sun and 1 AU. It turns out that the diameter of Betelgeuse is bigger than both the sun and bigger than 1 AU. So for the sun, we'll divide the size of Betelgeuse by the size of the sun. Betelgeuse is 1.4 billion kilometers. From today's office hours, I told you the diameter of the sun is 1.4 million kilometers. Class, can you tell me what the ratio is there? Here's a hint, 1.4s cancel out. Guess what 9 minus 6 is?
3. So it'd be 3 to 1.
What's the
10
answer?
to the third,
What is 10 to the third in plain English?
1,000
What are the units of 1,000?
kilometers.
False. Kilometers on top cancel kilometers on bottom. It's a ratio. There are no units. What does the 1,000 mean?
Oh, it's a ratio.
So 1,000 means what?
Be 1,000 to 1.
Say that, Caitlin?
Be 1,000 to 1.
1,000 to 1 is what?
Is the ratio between the size of Betelgeuse and the size of the sun. If you
Or
were
to put it more, yes, Caitlin, correct. A more elegant way to put it might be that Betelgeuse is 1,000 times bigger than the sun, right? Betelgeuse is 1,000 times the sun's radius. Okay, let's compare it to 1 AU. The size of Betelgeuse divided by 1 AU, Betelgeuse is still 1.4 billion kilometers. What do we have for 1 AU again?
$100,000.
No, that was a different thing.
150 times 10 to the 6
kilometers. 150 million kilometers. Let's do this. Last operation of the day. And then I can eat green curry. Okay. Come on, you bastard. 1.4 billion exp9. Sorry about the fuzz. Divide by 150 exp6. 9.3, but who cares about the 0.3? Let's just say it's approximately 9 times bigger than 1 AU.
Jesus.
Or 9 times bigger than 1 AU basically means that the diameter of Betelgeuse is 9 AU, if you think about it, right? Class, do you understand what that means? Where's my damn slideshow here from today? Let's go back to our solar.
Massive.
Sorry?
Betelgeuse is damn massive.
Well, mass is one thing, size is another thing. Let's not confuse the two things because they're not always the same. What I think you wanted to say is something like this. If you placed Betelgeuse, the red star, into our solar system, it would like swell. It would be like out to the orbit of Saturn, right? Right? That's what Betelgeuse is in comparison to our solar system. Stars have a wildly different variety of diameters. And, you know, we'll be learning about that eventually. But congratulations, you've completed homework 1. I know that took a little bit of time, but these things will get quicker as we go. And here's what we're going to do now. You're going to take a photograph of your homework, okay? All the little parts that I did, all this stuff had better be on your page or I will be angry and deduct points. Let's go over here and see how we submit the damn thing. Oh, no, I didn't want to do that. Oh, fuck. Okay, damn it. I hope that it didn't cancel my Zoom, so that's something. Sorry. Damn it, I'm gonna have to log into all this stuff again. I'm sorry here. Or maybe it kept me logged in? No, no, of course not. No peeking. Class, you probably already know what to do, but you know, how many people are in 101 and how many people are in 102? Let's see, Vincent, Caitlin, Emma, what section are you in?
I'm in 102.
Sorry, Caitlin?
I'm in 102.
Emma?
I'm in the morning class. I'm in, was it 1
001. Vincent?
001.
Okay, so there's 2 people in 001. That's where I'm gonna go. Get out of here. Don't like you. I got lots of astro classes. Don't forget to always tell me your class and your section. I have to say this to people all the time. What class, what section? I'll post the thing here when we're done today. And what you want to do is you go to the homework tab. You're going to click on homework 1. You're going to not do a write submission, but do browse local files and upload the picture. Yeah, you can see Caitlin doing it with her iPad there. Cool beans. And then upload that, okay? Let's see if any of you have actually uploaded yet. That's lab 1. Doesn't look like anyone's done homework 1. Okay. We should have even more than this. By Sunday, I want you guys all done. All right. See if anyone's done it here. Probably not for this one either. So annoying. Oops. Oh, looks like some people from the night class have done that. That's great. Makes me very happy. No one's done the homework yet, though. Okay. Anything from 600? Probably not. You guys are, who knows what you're up to. Grade Center. Someone in this class said they were from, who contacted me today? Was it Desiree or are you still here?
Destiny.
Oh, Destiny. Sorry. Destiny. Okay. So no one's actually uploaded the homework yet, but that's, I expect to see it in there somewhere. I should really not, I don't want to make this video go on too long here. I guess you guys are probably totally, oh, here, look. Vincent, how are we looking? Oh, I hate this. Yes, look at Vincent's paper. Picture perfect, Vincent. That's the kind of shit I want to see right there. If you ain't looking like Vincent, you ain't cool, all right? I want to see all, oh, Vincent, oh yeah, you got your 25 centimeter line. Look at that. Pro operation here on Team Vincent, okay? That's what I want to see. That's beautiful. That is a perfect problem set. That's what I expect from this class, okay? So that was lovely. So please try to make your work look similar to Vincent's. It's okay if your handwriting isn't as good as his. His was pretty good. I had fun hanging with you all. Hopefully one last look at this here before we go. That's only part of it, by the way. You should get the other parts as well. I will be seeing you guys on Tuesday. Once again, I'll send out the link just before 11:30. Is this format kind of working for folks here? Do we like it? Okay.
Yeah, I think so.
Good, good. That's the idea. So it can be crazy stuff, but we can do it together. We can make it manageable. We'll just plug along like this and everything was going to work out fine. So hit me up with any issues you might have. Otherwise, I'll see you Tuesday a little before 11:30 a.m. Okay? Don't forget to get calculators, rulers, and pencils. Peace out.